This conference will now be recorded.
That there was some issue and somehow I was not able to get through. Okay, so sorry for keeping you waiting. While I start, I'll just give you a little bit of flow what we are going to do today. So this is a hands-on session. I don't have any PPTs. Okay, so I will start little bit about Kaggle first. Okay, and then I will go and discuss about some of the algorithms. Okay, and when I say I will discuss about the algorithm, so I will focus on the implementation part. And my plan is that I will try to cover some from R and some from Python too, but of course we are crunched on time, so let's see how we can do that. Okay, so let me just pull out something I downloaded. Yeah, so first I will talk little bit about Kaggle. Uh, what you need to do is you need to go to your browser and type Kaggle, Kaggle, if you have not used this already. Okay, and so this is like called as home for data scientists. Okay, uh, so there are a lot of data sets that are available there, available over there, a lot of competitions available over there, and there are also a good amount of developer community. Okay, uh, so I will just start by taking you to Kaggle, and maybe I'll just share my screen. Okay, so let me just share my screen. Okay. Yeah, so let me first share this and then I will come back. So I hope you can see my screen.
Yes,
Okay.
sir.
Okay. So first of all, I would like to take you through one of the surveys conducted by Kaggle. Okay. And I will not just go through the entire thing, but I would like to highlight some of the things which is very important, especially for people who are planning to undertake their journey on data science. Okay. So this is particularly important for them. Uh, so essentially how they conduct this survey is that you see they have taken response from around 20,000 Kaggle members. Okay, uh, and there are quite a lot of questions. Even I am also one of the users who has responded. Okay, and there are very interesting results that comes through. So main important point that I want to highlight is, okay, so gender wise I don't give right now a lot of importance to that. Okay, this is a age wise profile of the data scientists. Okay, so you will see that there is a lot of the peak is around between 25 to 29 and 30 to 34, right? So that's where the peak of the distribution is. Okay, and country wise there is no prize for guessing that India tops with most number of data scientists. Okay, and now in terms of education, so a lot of time we feel that, okay, uh, do you need to get more degrees or something like that, right? So it turns out if you see this particular report, that actually many of the data scientists have higher degrees, like they have either master degree or doctoral degree. So that is actually 68%. Okay, so I don't know if you will take that as a cue to keep on learning for data science. Now this is a very important slide. So one of the questions I want to stop and talk about some time over here, that see this is something, this field is something which is like, ever evolving, right? So there are new kind of size we are talking about, right? The data set size is increasing. To handle that, we are talking about newer kind of algorithms, newer kind of hardware paradigms, and so on and so forth. Okay, so this is a very kind of moving target field, right? So you, every day something or other is happening. There are many things which are still at a research paper level, and then it is coming to actually in a packaged format. uh, so oh, what are the forums, or what are the things that people are learning from? So Coursera still stops, okay, uh, followed by Udemy, followed by university courses. Kaggle also has got its learn courses. They are also very good, but they are short courses, not very detailed ones. So they will be like 4 hour, 5 hour courses, okay, followed by DataCamp, edX, Udacity, LinkedIn Learning, and so on and so forth. But you get a basic idea, right? You get an basic idea that what are the main portals that to learn from. So if you ask me personally, right, that how do you partake a journey in the area of data science? So there is a distinction between the courses in Coursera and Udemy. I don't know if you guys have noticed it. So if you want to pick a subject, more theoretically, then you will go for Coursera. But if you want to really pick up the hands-on side, then Udemy is stronger on that side. So let's say you want to pick up time series for some of the domain tasks that you are doing. So you can very well combine these two. Okay, so that you learn the theory from Coursera. That's what typically I would do. Also try to find out some good books, some good lecture series. Okay, so machine learning, deep learning, for an implementation point of view, I will highly recommend the book by Aurelio Giron, okay, which is this hands-on scikit-learn with TensorFlow. Okay, and if you also want to have a, or you want to understand the underlying statistical techniques, so you want to give a lot of weight there. Yes, Shali, I will do that maybe, or I can bring that up later. Okay, so then you can look at the book. So the four words are okay, so I can type right here. Yeah, so what you can do is you can actually search by this term, okay, ISLR, and you can find a very nice series by Trevor Hesty, T. Shibrani, and all, okay, who are actually Stanford statisticians. So they have a book, uh, as well as they have a very nice lecture series around it. uh, but keep this caveat in mind that the book is much more thorough. Okay, and if like you have more of a statistics background, right, then there is another excellent book by them which is known by the name ESL. Okay, uh, okay, so uh, elements of statistical learning. So I will take that questions, okay, Shali, so there will be a time, I think. Okay, so now let's look at the experience curve. Okay, so there are people with a lot of experience too, but you see that 3 to 5 years, 5 to 10 years, this is also, there is a high stack. Okay, yeah, so you have said the correct book name. Now look at the machine learning experience. So this should actually give us some kind of confidence. So there are not a lot of people out there. So only there are people of, like, let's say 2%, 5% who have more than 20 years of experience in machine learning. So many are in the 3 to 4, 4 to 5, or 2 to 3 years of range, right? So it's not too late to start learning machine learning. Okay, so employment is something is important, right? The pay and everything, but I will probably share this link with you. and you can go through at your leisure. I will not go through this. I would like to quickly go through something else. So even median data science salary I am skipping. What I will like to take you to is enterprise machine learning adoption next. That how different enterprise are adapting to machine learning. And so you'll see that so these are actually 2018, 19, 20. So that's the legends are. And you see that the 2020 is growing. Okay. So probably like it should not be, but I do not know, and no, we do not use ML method has also grown. But at the same time, you see that we have well established ML methods that has gone up to 30.8%. So it is slowly growing. Okay. And so essentially we'll see that more than 60-70% enterprise for last 3 years are telling that they are either using ML, or they have started using ML, or they are at least exploring at least one model they have put into production. Okay. So this gives you an idea of the demand side. Okay. uh, so this is the spending again. This will be severely affected because the pandemic hit year. Okay. So not too much to look there. Okay. This is important. This is important that you need IDs, right? Integrated development environments to learn. So what kind of IDs you are going to use over here? Okay. So Jupyter Lab is the most popular IDE, and it is kind of telling you why, or justifying why I will show my hands-on on Jupyter notebook. So and then you have Visual Studio, PyCharm, Art Studio, and all that. Okay. So though they are also quite popular, you can see over here. Okay. But Jupyter Lab is really cool, and after I think maybe I'm not sure, maybe 2-3 years back. So if you look at my background, so I was a data guy. Okay. And I had mostly my experience around databases, different type of database engines like SQL Server, Oracle, MySQL, Teradata. And literally I have worked on tables which has hold like terabytes of data. Okay. So writing queries on them is really not easy, or application on them is really not easy. uh, then when I shifted to machine learning, so I started with R. I think that would be about maybe 10 years back, or maybe more than that. Okay. So when I was working in so that time I has worked in R, and R has some very big advantages. Probably when I will go into R, I will probably talk about that. uh, and then maybe around 2017-18 time frame, I shifted to Python and this Jupyter notebook environment. And they are really beautiful in terms of it is completely hosted in cloud, and you don't need to really maintain anything for yourself. Okay. The installation is taken care of. You don't have a downtime. You have access to GPU and TPU. All new libraries are there. The data sets are also in that environment. So it is really very good. So the most important way, or most easy way to use it is uh, collab using this collab platform, Google Colab. uh, so as I have a bias towards this Kaggle, so I generally use the Kaggle notebook environment.
Right
But
in
it is
that window. Kindly everyone click on that and try to.
and it's you will see that the environments are very similar. Okay. So this will give you an idea that which IDEs you should focus on, or you should first start using. Okay. All right. Now methods and algorithms. Okay. So you see lot of now we are much talking about this deep learning models, but you will still see that the most important models, okay, are people are still using, are this linear or logistic regression, and followed by decision tree, random forest, then gradient boosting. followed by CNN, then Bayesian, then recurrent neural networks, and so on and so forth. Okay, so probably that will again make you understand that why organizers have given so much of importance on regression, decision tree, random forest kind of methods. Okay, all right. I think this is the last slide I would talk about this particular survey. Okay, so which are the frameworks which are important? Again, why it is important is that if you have to pick a choice that okay, I will master 2-3 frameworks or 2-3 tools, so which are the ones that will pick up? So you will pick up scikit-learn, TensorFlow, Keras, XGBoost, and PyTorch. Okay, so this is what you are going to focus on if you are looking at the top 5. So now you probably spend a little time. Okay, I want to go back.
Hi, sir. So since you are talking about know about data science or how to data science, so I just wanted to bring up one question like how to build portfolios when you are doing projects, how to include them in your portfolio and your CV, sir. I mean, you can just talk about this at the end of the session, just a little bit.
Yeah, sure. Just remind me then. Okay.
Sure, sir. Sure, sir.
Yes. I'm just stopping sharing. I will just share something else now. Okay. Or maybe while I do that, I will talk about your question. So generally, best thing is to have those whatever you are doing in your GitHub. Okay, and once you have that in your GitHub, you can share in your social media handles about your GitHub profile. And you can also, as I said, have your Kaggle notebook, share with everyone. So there is a concept of popularity also, like how many people are upvoting and everything. Okay, so you will have to, so if your model is really good or notebook is really good and understandable, so you need to share with your friends, popularize it, and people will start taking notice. Okay, so let me share my screen now.
Thank you, sir.
Yeah. So I hope again my screen is visible.
Yes, sir.
Yeah. So how do I close this? Because I don't see. No. Actually, I'm not able to go to the edit mode. Just 1 minute. Yeah. Now I can go. Perfect. Okay. So this is the environment. So this is a typical Jupyter notebook environment. Okay, I will probably show at the end that how you can find or create a notebook like this. But let's just assume that you have this notebook created. So let me go through this and then I will come back and tell you how to create a notebook. Okay, so this is a Jupyter notebook, as you can see in the screen. And one of the things I like about this is, uh, there are two kind of cell. Okay, one is called as the code cell and another is called as the markdown cell. So code is self-explanatory. Markdown are the cells that you use to explain what this code is going to do. Okay, so this is a beautiful thing because everything is in the web in form of a link. So let's say you are doing some work for your client. Okay, so you can have just the POC done here. Even without a laptop, you can walk in your client's place and you can show him everything. Even if he is a savvy client, you can probably just give him the link and he can look at what kind of models you have done. So now also all the research projects that we are doing with research scholars, right? So we are working in this environment. They will just probably send the code to us or link to us, and we will work with them together. If there is a need to change something, so we'll tell that. So a very good collaborative environment. Okay, All right. So you see, this is here is the option of plus code and plus markdown, which just tells you that you can create new code cells or you can create new markdown cells by this. Okay. Now let's go ahead and look at the problem that we are going to implement. So this is a problem that we have picked up from ISLR, the book I was talking about. So pay close attention to the problem setting. So there, an organization actually wants to increase their sales by increasing their media expenses. So the advertisement they are making in different media, okay, so they want to increase that, and as a result they feel that their sales will also be increased. Okay. And typically in the data set, so please understand that in a machine learning problem, so please forgive me for those who are quite advanced, right, in this. So I will just break it down little bit. So any machine learning problem. Okay, so Shaili says not audible. Is it the case with everyone?
No, sir, you're audible, sir.
Okay, okay, okay. Thank
So
you.
audible.
Okay, okay, okay. All right. So now any machine learning problem or data science problem, we'll start with a data set. Okay, and this data set will be arranged in rows and columns. So this is something probably I have discussed in my previous session also, and you have seen that. So typically in this particular problem, then what will happen, that for each of the stores, right, so my each row will correspond to one store. So if I'm 100 row in my data set, then actually I am dealing with data of 100 stores. Okay. And what I have over here, I have corresponding TV advertisement spend, radio advertisement spend, and newspaper advertisement spend. These are my input attributes, and I am going to use them to predict the sales. So sales is my target variable, and this TV, radio, newspaper is my input variable. So which are often called as features, attributes, predictors, regressors. You may also hear a term like covariates. Okay, so based on your background, like what discipline you are coming from, you will give different names to it. Okay, so this I think you already know, but just a very quick refresher, that regression technique. So you already know that when you pick regression, when your input variables are numeric and the output variable is also numeric. I hope this is at least crystal clear to you. All right, now if you look at regression, how you can further subdivide these methods. So you can divide it in terms of number of independent variables. So very odd case you will have only one variable that is involved. If only one independent variable is there, what do you call it? You call it as simple linear regression. If you have more than one variable, you will call it as multiple linear regression. Okay, now let's look at the shape of the regression line. So based on the shape of the regression line, it can be linear. You can add adding a level of polynomialness, if I may say, to it. And you can even regularize it, right? You can even regularize it so that your output is not affected by some extreme changes in the input. Okay, so for that you bring in lasso, ridge, all these kind of regularizers, and then the classic combination of lasso and ridge, which is called as elastic net. And then also in type of dependent variable. So if the type of variable is actually, as I said, is actually numeric, then it is this regression family. Also there is one particular method where the output can be 0 and 1 and we still call it is regression, is the logistic regression. Okay, So now let's go ahead and start looking at the libraries. Okay. So basically, I will not have time to explain how these libraries work, but pandas is one of the important libraries if you want to use Python. Okay, so it deals with all kind of getting data inside your system, right? So if you don't get your data inside, then probably you cannot do anything. Okay, what is NumPy? NumPy is a specialized library again, because these data are all numerical arrays, and you can store them in multidimensional numerical arrays. So NumPy is a specialized library to do operation on that. Okay, so matplotlib, as the name suggests, it is for visualization, and similarly seaborn is also for that. Now you see that we were discussing, uh, we have something like a trend test split. Okay, because we wanted to avoid overfitting, so we need to import that. Finally, we need to import this model linear regression. We need to look at that how we are doing as far as the model performance is concerned. So we have spent quite a lot of time the last day on model evaluation too. So this will help me to look at this particular evaluation measures. So sklearn actually is the important library which has all these algorithms. Okay, so which we also called as the scikit-learn. Okay, so sk is the short form of scikit. And if you really want to pick up machine learning using Python, so the top 5 libraries are going to be sklearn, pandas, numpy, matplotlib, and seaborn. Okay, so these are the 5 libraries which you can see over here. And I have used that model because I want to evaluate the model, or I want to see the how good or bad the model is. So first of all, every time what you should do is you should actually start by importing the data and inspecting the data. So essentially, I have already this data available in this environment. Okay, and I am using this pandas library, you see, and there is a function called as read.csv. So this read CSV file. I hope you know what is a CSV file. CSV file is a short form of comma separated values. So essentially, you will have text file where the columns will be separated by commas. Okay, so these type of files are more generally called as delimited files, and comma is not the only delimiter. You can use tabs, you can use other delimiters as well. So to run it, it is very simple. You see here is a play button. You just click on it and this will start executing. So what all we are doing over here? So first time it is taking a little bit of time because it is downloading the data. Okay, so it is giving me an error because I have not run the import libraries. So you'll have to go sequentially, of course. Okay, so now I will run this. Okay, so now you see that first what I have done is I have printed. So print is very similar to any other programming language. Dataset dot shape. So it will tell me how many rows and columns are there. Okay, so basically it is telling me 205. Okay, so 200 rows and 5 columns. But I expected actually 4 columns. So what has happened is, you see that there is a serial number kind of a column which has come, which is not important for my analysis, right? So it is not my input attribute. Okay, and this dataset.head actually allow you to take a look at the data. So you look at the top 5 rows. Okay, so one good thing is actually looking at some kind of visualizations. Okay, and to especially look at relationship between two numerical kind of variables, we use the scatter plot. Okay, so please remember, because these visualizations are important. Okay, so this is my target variable. I'm just looking at it, and one of the ways to pick up some of the rows and columns is using this particular notation, which is .ilog, which stands for index location. And I don't know if you can see, So it has two parts. While in one place you can mention the rows, another place you can mention the columns. Okay, and here what you are saying is that I'll pick up the fourth index, which is actually the fifth column, because Python is zero index, and you will take all the rows. So this is just to show you how you can look at a particular column's value. So the scatter plot is in the next line, and here we are using matplotlib. Okay, so basically I am using subplots over here because you can understand what subplot means. So a plot will have separate sections, right? And in each case what I'm doing is, so just focus on this line. So first I'm plotting, doing a scatter plot with the variable, the second variable, which is maybe the advertisement in TV. The next is radio, next is the newspaper. So what is changing among these three, you see, like, is the code visible, or I need to zoom, though it will be a little tricky for me,
That's
but
visible.
Absolutely visible, sir.
okay, great. So if you look at this particular, just focus on the scatter plot, scatter command. Okay, so you will see that it is changing from the first column, second column, third column. However, we have kept the fourth column as fixed, because what we want to see is, we want to see that out of these three advertisement spends, which is more related to sales. Okay, so let me do that. And so you see the columns, like the scatter plots. Okay, so what is your conclusion over here? I want to hear some of your conclusion.
So for TV versus sales, it's pretty clear that they are having a positive correlation, right? And same goes for radio, but there is still a randomness that is appearing. And for talking about newspaper versus sales, there's a lot of randomness, so it's very difficult to find any kind of correlation between both of them.
Perfect. So your conclusion is in the right line. So looking at these three, we can at least conclude that TV is the most dominant media. Okay, so this is one of the very important thing of linear regression kind of models, right? Because the models are interpretable. Okay, uh, so I'll just it is not really regression revisiting, but I'll just tell you how regression works very quickly for this particular example. So here you see that the TV spend is plotted in x-axis, and sales is plotted in y-axis. So what we want to do is, we want to plot a line, right? So this blue line you see, so this is my model, and these red circles are actually the data points, the actual data points. Okay, and so these projections that you see for any particular point, so these are the errors, and you want to minimize the error. So you want to get a blue line such that these errors are minimized. And typically when you have one variable, it is represented by your straight line kind of a thing. Okay, so it is like y equal to mx plus c, or uh, y equal to a plus bx. So in this particular case, like in ISLR, you will see the notation y equal to beta 0 plus beta 1x. So like it is one and the same thing. Okay, essentially you want to find out beta 0 and beta 1. You want to find out beta 0 and beta 1 such that this line is best fit. Okay, the error is minimized. Now I have a question over here. Okay, so can you tell me how do we determine this beta 0 and beta 1? Who can tell me that for linear regression, how do we determine beta 0 and beta 1?
Least square method.
Sorry, what method?
Least square method.
Least square method. Yeah, least square method. Okay, so what she correctly says is that one of the method is least square method. So basically same thing we are talking, that the residual, we are saying that these are called as the residuals or the errors. This we want to minimize, but then the positive residual and negative residual can cancel out. So we take the square of the residual and we try to find out value of beta 0 and beta 1, which makes the square of the residuals minimum. So that's why you are calling it as least square. That's okay. uh, so one of the ways to solve it, you can have equations, right, from your statistics and calculus knowledge. So if you want to maximize something or minimize something, you can set the derivative at 0, the first derivative at 0, and solve the equation. So there are two variables over here, right? So you can have two equations, and you will probably do a partial derivative, okay, because it is a multivariate problem. But one thing that at least when I was a student I always failed to understand is, then why do we also use gradient descent? Why you use approximate methods? So these, we have a very clear kind of equations available which we call as closed form equation. So why we don't use the closed form equation and go for some kind of methods which are like gradient descent, where we start from random weights and then we try to find optimal weights. The reason for the same is that when you have a large data set, you cannot take the entire data in the memory and use this closed form kind of equations, okay, and then there can be so many more variables involved. So that's the reason you start from a random kind of weight, and then you apply gradient descent looking at how how you are doing on the errors. So you should try to find parameters such that your error is getting minimized, okay. All right, so now let's see how we can feed the model. So first what we are going to do is we are going to select the input and output variables, okay. So what we have done over here is we have picked up the second column, the third column, and the fourth column, okay, in the input, okay. So we are using the same nomenclature of iloc, you see, and we have kept the fifth column as as y. And those who are seeing the Python syntax for the first time, you might think that why 4 is included in both the places. Is it a mistake? No, it is not a mistake, because Python follows this kind of a notation or syntax that it is up to 4, not including 4, okay. So basically it will include 1, 2, and 3. So I have taken x and y. Now what I'm going to do is I am going to uh, initialize my linear regression model, okay. I am calling that model as a regression, and then I am doing a trend test split, okay. I'm doing a trend test split. You already know why we are doing that. So for that we are using a method trend test split, and this does a very nice thing. It it returns x trend, like, so the training set, its corresponding y variables, y trend, the testing set, and its corresponding y variable. So all these 4 it can return in one shot, okay. Look at the parameters over here. So we have supplied the x and y, the input and outputs that we have just assigned, and we are saying the test size is now 0.2, okay. So what that means is that 80% of the data you are using for training and 20% you are keeping for testing, right? And please understand that this will be generated through random sampling. This is no sequential assignment, and we have mentioned that random state is equal to 0, okay. So can you tell me that what is this meaning of random state equal to 0?
So there is no pattern in selecting or picking up the data points. I mean, for example, if there would have been 1, 2, 3,
Mhm.
the random state or the random seed, then it
Mhm.
would go by that order. I mean, I'm not able to explain it very clearly, but
Okay,
that is what it is.
okay, okay. Anyone else want to try? This is also very
Good
important.
good morning, sir. I would like to give it a try. It may mean like if we are having suppose 100 rows and the random state is capped like 5, so we'll be picking every fifth row for our test set or something like that.
No, no. So basically one of the problem is, okay, so if you remember our discussion from bias and variance, okay, uh, So recently I was doing an experiment with decision trees just for my purpose, not for any paper or not for any class assignment, but even for a simple data set, uh, if I create a random sample, right, you can create a random sample in many ways, right? uh, so the random sample that I will pick and the random sample you will pick will be very different. So if your boss has given you a task or your supervisor has given you a task and you say that your model's accuracy is 80%, okay, and your boss runs it, there is a possibility he gets it as 65%. Why it is so? Because his random sample and your random sample is different. So this is a very, very important point. Okay, but if you fix this random state, then that will ensure that he will also take the same random sample and he will also take the same random sample. So this is very important for reproducibility of the result. Is it clear to you?
One question, sir.
Yes.
If the random state is set to, for example, you say it defines the randomness, right? So if I set 1 2 3 and
Hmm.
I'm getting a result of or a prediction of 85%, and if my colleague is also using the same random state, right, say 1 2 3, and he's also getting the same prediction, so isn't it that we are just we are just killing the randomness here, because
No,
randomness means.
absolutely not. Absolutely not. Absolutely not. I think you are not understanding it correctly. See, randomness is fine, but if the randomness is so, let's say you have built a model and you want to put it in production. Okay, so now can you say that okay, the results will be random?
No, sir.
You cannot, right? So that's what we are trying to do. So when you are doing your experiment, so if you look at the other notebooks, probably I will share with you. Okay, so you will see that we don't try with one seeds. Okay, so we will try with many other seeds. So these are called as seed values. Okay, and we will report the average. But if you want to let's say you are trying to troubleshoot a particular thing, that for a particular seed value you are getting a very low error. So if you want to debug it, how will you debug it? If every time your result changes becomes random, are you getting what I'm saying?
Yes, sir. Yes, sir.
So that is what, if you want to fix that, okay, uh, it is random, fine, but I should be able to generate that random thing if I want to dig deeper. Okay. uh, yeah, so random state equals to, someone has asked that why state equal to 0. Now this is something very arbitrary, you can use any value. Okay, so if you many cases you will see that we are using a value like 42. Okay, that is a standard default value. So it only ensures that if I am using 42, someone else is using 42, I will get the same set of rows, that's all. Okay, so next is this is the model that we have initialized. We'll use this fit statement. So this is common with all sklearn models, and I am giving the X train and Y train because you know that I am going to train my model on the training set, right? Okay, so let me inspect the model. So if I just, okay, I have not run this, so let me run this. Okay, so it seems like I have not run the earlier one also. So this happens generally, when you are explaining and then you get, yeah. So now let me look at the model. Okay, so basically I wanted to show you something else. So if you give a dot and press a tab over here, okay, so it will tell me that what all you can see probably, right, what all things that are available. So if I just run this coefficient, okay, so you see that I am getting getting some coefficients over here which are nothing but those beta 0, beta 1 and beta 2 values, right? So if there are 3 variables, then how many unknowns I have 1 for the intercept and 3 for uh, 3 for these 3 variables, right? 4 values. So coefficients are for the three coefficients. Okay, intercept you can get separately. So this is what I have done in the next step. So I have printed the intercept and coefficient. Okay, so all is coming in this regressor dot nomenclature. Okay, So far so good. Now what I'm going to do is I'm going to use it on the test data set. Okay, so how I'm going to use it? There is a very simple method called as predict, which I'm going to apply on this regression model. So regression model now have already calculated these parameters, and I am giving the X test as an input. Okay, and then what I'm going to do is I'm going to create a pandas data frame where I will keep the actual value as well as predicted values, and then I am going to just put a scatter plot and see how my actual and predicted are differing. Okay, so this is how it looks like. Okay, so any interpretation of this? So let me repeat what we are trying to do. Maybe you might be lost because there are so many new things I'm introducing you to. So you understood that we are doing a, so let's go to the first context, that we are doing a regression problem. We are trying to predict the sales based on these 3 advertisement media sales. Now from last day we have understood that to avoid this kind of overfitting, we need to split the data into training and testing. So we have trained our model. Now we are testing it on our testing set, and what we have done over here is we have plotted the actual sales value on the testing set and what the model has predicted. So this particular graph is just giving you that. So now can you help me interpret this?
I'm still trying to figure how.
Yes, positive correlation. I got an answer. Yes, yes. So at least you can see that when the actual has grown, the predicted has also grown, right? So our model is working. So it is not that it is going in some other direction or it looks completely random, right? So this kind of give you some visibility or understanding that this works. Okay. So now I am going to go to another important thing about the models. Okay. So which is about some of the statistical parameters. So you'll see something like R squared, adjust R square, if statistics, t values and all that. Okay. So specifically, I would like to focus on this t values and this p values, right? So any of you know about this t value and p values? I'm sure some of you. So let me tell you anyway. Okay. So I told you, right, that these are samples. Okay, these are samples, and even if you get a good coefficient value, okay, it may not be statistically significant. Are you getting what I'm saying? Okay, so for that what you use is you use this t distribution. Okay, so there is some reason. Okay, so if you read about t distribution, f distribution, chi-square, normal distribution, right, so if your random variable has a certain format, then you can use certain kind of variable. Okay, like t distribution, if I'm not wrong, it is like if you should take a square of a random variable. Okay, and then you take a square root, then you use a t distribution. Okay, so because error will also take a form like that, right? But let's not go there. Here the most important thing is just reading about this t values and p values. Okay, so basically, if you go back to your statistics, okay, if you remember, there are 2 things. One is called as a null hypothesis, another is called as an alternative hypothesis. And do you know what is this p value tells you? The p value gives you the probability of null hypothesis being true. So let me repeat, what is the p value? P value is the probability of the null hypothesis being true. Okay, and what is the null hypothesis? So in this case, actually for each variable you set up a hypothesis testing. The hypothesis setup is very easy. It is like the null hypothesis is TV is not important for TV is not important for sales prediction, that is the null hypothesis, and the alternative hypothesis is TV is important for the prediction of sales. So now if you look at the p values over here, right, so you see that the intercept term, the TV radio has very less p values. So that means this has a bearing on the sales, whereas in newspaper you have a very high value, okay, which is 0.653. Okay, so you see that whatever you are seeing visually, your model is also telling you the same thing, that newspaper is not probably very important for the model. Okay, so could I give you some idea about the p value? So what we will do is that now let me take it at a very layman term. Okay, so let's say you are building a regression model, you have 5 variables, and you have got all corresponding p values. So if your p values are small, then that variables are if p values are small, that means if your p values are small, that means that variable is important. Okay, so someone is asking that what is the null hypothesis. So if you want to learn machine learning data science, you will have to look at some basics of linear algebra, statistics, and calculus. But so one at a very high level, what I can tell you is that null hypothesis is like telling so how statisticians looks at a model. Okay, the statisticians look at a model, the null hypothesis is this model is not valid. Okay, so if it is not valid, we can say that it is null, right, in that sense. Okay, so that's what we do over here. That's what we do over here, that we say that this model is not valid, or this variable is not valid for this model. So that is your null hypothesis, and your p value tells you the probability of the null hypothesis holding. So if you want a variable to be important for your study, okay, can you suggest book for basic? Shaili, please hold on to your questions. I'm getting little carried away by your questions, so please don't mind. Okay, uh, I will answer all your answers. No worries. Okay, all right. So I hope you have understood at least this much. I hope you have understood at least this much, that okay. Can you see my screen?
Yes, sir, it is blue,
I don't know
pure
what
blue.
happened. I don't know what happened. Yeah, no screen. Okay. Yeah, I don't know. Just give me 1 minute. So I don't know. Okay. So let me repeat what I was discussing. That essentially this p-value will tell you which variables are significant and which variable are not. Okay. I will just quickly open the Kaggle notebook. Again, sorry about that. And probably this time I will share all my screens. So this one, let me open this one. Yes, I have got that the screen is not visible. Yes, I have understood. So let me again share my screen. Okay, I think this is not the one that I was doing. Do you see my entire screen, or how it is?
Yes, sir, we can see a Google page.
Okay. So yeah, so we are now at the so we are now at the end of linear regression. Okay, so basically, let me, I don't know, it is just actually, how do I close it? All right, so I actually was at the fag end and was explaining you over here, okay, that how to interpret this. So there are some assignments over here. Those who are really interested, you can do the assignments, and I promise you that if you get stuck and I know give your assignment results, so you can actually put your assignment results in the comment section of this. So if you get stuck, I can be late, but I will definitely respond to all of you. Okay. All right. So let me, for the sake of time, go to our next notebook, which is a clustering assignment. I hope you can see this k-means and hierarchical. Uh, uh, do you see this notebook, k-means and hierarchical clustering?
Yes, sir.
Okay. Okay. Perfect. So one of the things, as I said, is about this notebook is, you can carry the code and documentation in the same thing. Okay, and we have already discussed clustering. I have only discussed, so I'll not, explain them here. But essentially you got an idea that you want to find natural groups, and no, like no natural groups, or no arbitrary kind of natural groups. You want certain things. The things are that you want this inter-cluster distance to be minimized, and the intra-cluster distance within the cluster distance to be minimized within the observations, which you called as cohesion, and between the cluster you want to maximize, which you called as the separability. And we also discussed that how the idea of clustering or number of clusters is ambiguous. Okay, we also discussed that there are essentially two type of clustering. One is called as hierarchical clustering, like the one you see over here, and another is, your partitional clustering. Okay, some of the use cases is also mentioned over here, that how you can use this in telecom, right, where you want to group customers, because if you want to give a particular kind of offer, okay, that may be suitable for a set of users. So for that you want to maybe find out the groups. Okay, uh, now you can use this for fraud detection. So many times, there is a particular problem called as anomaly detection. So you apply clustering for that. So generally a very low populated region or low density region, okay, a low density region is actually the outlier regions. Okay, so I'm again not going into how k-means work, because this is something I have already discussed. Okay, so I'm going to use a very simple data set over here. Okay, so let me just use this data set. Okay, the first time the data just takes a little time to load, and I want to give you a look at the data directly. Okay, so this is the data you see. Okay, so you have few rows and few columns. So it has 14. So basically, like each row represents one individual. Okay, and there are two attributes which are using to describe that individual. So you have age and salary of that individual. Okay, so these are the two attributes that you are using, and you want to find a natural group of these users, or these persons, these individuals. So first of all, like the last case, what we are going to do is we are going to do a scatter plot. So you see we have done a scatter plot over here, and looking at this particular scatter plot, can you tell me, do you see any natural groups? I have not performed any clustering, but do you see any groups over here?
So age 70, between
So
68
you
to
see a group.
75, there's a group. Yes, sir.
There's a group. Okay, okay,
Then
excellent. So I'm getting good answers. So you have really followed this. Okay, and I hope everyone, so some of you are answering, but I hope everyone of you are getting it. So yes, I mean, we can think that yes, there is a group, as you, some of you said, and then probably here you can think there is a group, here you can think there is a group, right? Okay, so, and what is the semantics of the group, right? So it is very important, especially many of you who are attending have a lot of maturity, so you will not do these rookies mistakes, right? So we apply groups, we have clusters, then we cannot explain that to the end user or to the customer. It's very important, right, that you are able to explain that. So probably the explanations are like this. So above 70, these people are probably pension holders, so that's why their salary is in that range. Okay, and then there are some people who are early starters, so their salary has just started growing, maybe this region. So uh, and then maybe these people are top level executives, okay, who are like quite senior position in their career. Okay, so maybe these are the semantic understanding of the clusters. Okay, so I am using the same notebook, but I am using a different programming language, which is R. Okay, so R is a open, like Python, it is an open source programming language. And if you look at only data processing and machine learning libraries, R is much more stronger than Python, much more stronger than Python. Okay, in terms of number of libraries that you have available, especially in terms of, as I said, data processing, different statistical tests. Okay, Python is just no match. But when you come to larger type of data, unstructured data, okay, images, text, deep learning, Python is again way ahead of R. Okay, so it is not necessarily. So I have a very favorite researcher of mine, okay, who works in this area of bioinformatics and deep learning. So a lot of the processing of the data he does in R, and then he uses Python, this scikit-learn TensorFlow, to train his deep learning models. So when you are thinking of a pipeline, you may have to use both of them. Okay, whatever library are good for that. So that's why we thought that we will show you both. And as it is also in this Jupyter notebook format, so that's the beauty. You don't need to learn the environment separately, like RStudio or PyCharm or something like that, right? So we are using the same environment. And see, this is the syntax of k-means. Okay, now last day I did not discuss about this. So is k-means a randomized algorithm? First of all, what is a randomized algorithm?
Yes.
Yes. So why do you say it is a randomized algorithm?
In the start, we have to randomly select the seed points.
Perfect. So basically, again, like this training test testing set case, you are starting with randomly selecting the seeds, right? So there is a randomness that is involved over there. So that's the reason I again may get a different set of clusters, and you can get a different set of clusters. So for that you have this parameter called as nstat. So nstat means that how many different starting seeds you are experimenting with. So you can have this nstat as different as different, so you can have as high as 10 or 25 or anything. Okay, and iter max is actually how many iterations you are going to run for. So I was talking about convergence, right? So one of the thing is, of course, you give some convergence criteria, but easy thing can be you let it run for some maximum number of iterations. Okay, so here I am going to run this clustering on this data frame. I am going to ask for 3 clusters, and I am going to choose of 5 different starting points. Okay, and then what I'm going to do is I'm again going to draw the scatter plot. Okay, I'm again going to draw the scatter plot and see that how the clusters are doing. So the results are out. Yeah, so the clusters are marked in different color. Okay, so this is a green cluster, this is probably, you can see, a deep blue cluster and a red cluster. So is it in sync with what you guys were thinking? Is this a cluster that you are expecting?
So the two clusters in the middle, sir, it is clear. The cluster in the right corner is also clear, but the cluster in the first cluster of of the two data points, which is syncing with the last cluster, is a bit of dilemmatic.
Okay, so so maybe most of you are saying it is no. Okay, most of you are saying it is no. Now can you see what is happening over here? Actually, if you look closely analytically, you will see that this particular variable age is not playing any role at all. See, if this is below certain value, then it is green. If it is between, let's say, 42,000 to something, then it is this a dark blue, else it is red. So this is what I was telling in the first class, that when you are using any distance based algorithm, if you don't bring them to same scale, one variable will dominate the other, and that's what is happening over here. So for that, what you will do, you will apply a scaling. Okay, uh, so these are some ways you can inspect some of the properties, right? So you can so if you do a km.out and km.out.center, you can get the cluster means. Okay, so this is saying the cluster mean is 33 years and 63,000 of salary, and so on and so forth. And this clustering vector is telling that out of those 14 observation, which belongs to each cluster. Okay, uh, for the sake of time, I'm not again going in more of it. Okay, all right. So basically, I don't know where I have kept it, but anyway, so what I actually need to do is I actually need to scale this particular variable. Okay, which I have not done over here. So your assignment can be to actually scale this variable, okay, and see whether the clustering is working perfectly or not. Okay, so there is also some more materials over here where we have shown you, okay, where we have shown you that uh, where we have shown you how you can do a clustering on this iris dataset and find the actual good number of clusters. Okay, so if I just run this iris, so this is a very famous dataset, very old dataset, we use a lot, where you have data about flowers. Okay, and this data, uh, individual rows belong to one flower, and you use different attributes to describe them. Okay, so you have these 4 input variables: sepal length, sepal width, petal length, petal width. Okay, and you have also a corresponding target variable. So you can understand that if we want to ever do clustering, we are not going to use this species type of variable. Okay, so basically what we do is, what we are using this experiment for is, let me run it and I will explain. So what I'm doing is, I am running k-means with different choice of cluster values. The cluster values varies from 2 to 10. Okay, and for each one of them, I am calculating the sum of squared errors. Okay, and the idea is that wherever I will get a elbow kind of a shape. Okay, so you can think that this is a elbow kind of a shape. Okay, after that, maybe the sharp drops are not there. You can even think this is a elbow kind of a shape. Okay, so you stop there. Okay, so you say that this is my optimal number of clusters, and this diagram is called as the elbow diagram. Okay, so what we are doing is, we are we are running the k-means algorithm with different values of the cluster, and we are plotting this sum of squared errors. Okay, so wherever we are seeing a sharp drop, we call a elbow is formed, and that we take as the optimal number of clusters. Okay, so two things we discussed using R. One is that how you can take the data set and use k-means, and then how you can use the optimal number of clusters. Okay, so I'm not continuing any further on this. So can anyone from the organizers tell us how we are doing on time? Will I have like, do we have a kind of hard stop at 11:30 or?
So, no hard stop, sir. The first lectures generally go until 11:40, around 11:40 p.m. and the
Perfect.
second lecture starts at 11:45. So we have time, sir.
Okay, okay, thanks. Then what I will do is I would like to show you another notebook, okay, which is the KNN. Okay, so I hope again you can see my screen. So now I am not going to again explain you the libraries. I'm just going to run this, okay. And here we are going to apply this on a data set called as breast cancer Wisconsin. Okay. So what is this typical, what I have in this data set? So features are computed from a digitized image of a fine needle aspirate of a breast mass. Okay, so they describe characteristics of the cell nuclei present in the image. Okay, so the dataset description is like this. I have this ID number, so which typically will tell you the patient number. Then you have the diagnosis. Okay, so whether you know that breast mass tissue is of type malignant or benign, and so M stands for malignant, B stands for benign, and then I have some input attributes which are again characteristics of the cell nuclei which you have extracted using some image processing technique. So this image processing technique is out of scope for us because this data is already given to us. And like every time, we'll first import the data. Okay, so you just need to give the name of the file, and whatever we are doing earlier, we'll try to do that. Okay, so I have now 569 rows and 33 columns. Okay, and these are my this is how the head looks like, right? So you have the ID field, you have the diagnosis, and then there are many numeric fields. Okay, we can see again some extra field which has come here, which so shows to me at least, or seems to me at least to be a junk value. It is giving me values like not a number. Okay, and look at this describe. Okay, so this describe actually gives you some descriptive statistics about this particular attribute. So here we have applied on the second column. Okay, so it is telling me how many counts are there, how many unique are there, which one are which is my top one. So this is actually telling me that 357 benign cases are there, so naturally 212 uh, malignant cases are there. Okay, in the next statement we have described the next a few more kind of numerical attributes. Okay, which are like radius mean, radius mean, texture mean, perimeter mean, and so on and so forth. So next what I'm going to do is, so scatter plot is one of the important visualization plots, and if you really have to learn couple of plots, the other plot is going to be box plot for visualization purpose. So what you do in box plot, I think it is seeing and believing. Let's do that. First, let's look at the example and then I will explain. So what we have done over here is, probably now you can understand that I have taken two input attributes, texture mean and perimeter mean. Okay, so this is what I have mentioned over here. And then what I'm doing is I'm trying to look at the spread of the spread of the values. Okay, I'm trying to look at the spread of the values across these classes. Okay, now again a conceptual question to you. that looking at these two attributes, so one attribute is texture mean, another attribute is perimeter mean. Can you tell me that which attribute will be better? Okay, which attribute will be better if I want to build a classifier? Can it be told? First of all, tell me that.
It appears that the second graph or the second box plot has
Mhm.
high variability
Okay,
in comparison to the first one.
okay.
And talking about classifiers, I think the first one would be better if it is
First
built,
one.
because I am not got data on classifiers right now.
No, no problem. No problem. I want to hear out your intuitions. Anyone else want to try?
So classifiers can be built on the second one, sir.
Okay. Why do you
So
think
why?
so?
So because there is a variability, but there is also different clusters, because at 25th percentile, at 50th, and at 70th. So there are different clusters forming at these percentiles.
Okay. Okay. So for many of you, it may not be clear at all that what this box plot is doing. Okay. So I understand that. So let me just give you a formal definition what box plot does. Okay. So you see, so this is just, horizontal and vertical representation. So one and the same thing. So the box represents values between Q1 and Q3. So you have the median, you have the Q1, Q3, and so this is called as the box, and these are called as whiskers. So what is this whiskers? Whiskers are actually Q3 plus 1.5 into IQR. Again, what is IQR? Interquartile range, which is nothing but Q3 minus Q1. Okay, so anything goes beyond, so you create a whisker over here and a whisker over here. Anywhere, any value which goes beyond this, you call it as an outlier. So someone was telling that it can be used for outlier. Yes, so box plot is typically used for finding univariate outliers also. Okay, anyway, coming back to what we were discussing, right? Coming back to what we were discussing. Uh, so typically you can understand then that, so this just tells me the spread of values. Okay, that how in benign class the value of perimeter mean is, and how for malignant class my value of perimeter mean is. So that's what it is telling. Now if you revisit, you will realize that you want those features which actually has good separability between these two distributions. If I call these two distributions, right, that my malignant class values and my benign class values should not overlap, then my feature is good for classifier. Do you agree now? Right? So you can probably now say that this is a better attribute, the second one, right? Okay, so like I was like I built my other model, I will build my this model also, and I don't need this ID column and this last column. Okay, so what I'm going to do is I'm going to drop them. I may not have dropped them and used like I have used in my advertisement example, but let me stick to this process now, or adapt this process now. And what this axis tells that I'm dropping columns. Okay, so let me just apply this. So see the two columns are dropped. So now my shape is 569.31. Okay, so it is no longer 33. Now when go to the fitting model, okay, again I am going to put it in Y and X. Okay, and like k-means, KNN is also a distance based algorithm, so we are going to apply scaling. So there is a there are some definitions I have given over here which you can go through. So this is how you take a scalar quantity and then apply on the entire data. Okay, so this is what we are doing over here. Okay, and we are getting the value in X scaled. So now you see the all the values are somewhat looks like between 0 to 1. Okay, so all variables are now having similar weightage. Okay, and then we will use the same kind of training testing split as we did in case of our linear regression. Only in clustering we did not do it because it is not supervised and there is no question of kind of overfitting and everything. Okay, now we are going to use fitting the model. So how many neighbors we are going to choose. So by default it is 5. The weight is uniform. So if you remember that we were also discussing, we can assign different weights to different neighbors based on how far they are from a particular point. Okay. uh, and you can, what kind of distance measure you are going to use. So this is more of the more of the core algorithm implementation. So I'm not going to that. But p equal to 2 and metric equal to Minkowski actually tells you what distance measure you are going to use. So actually you will see that Minkowski is a general form of distance measure, and when you apply p equal to 2, this converts it to Euclidean distance. Okay. So Euclidean distance is the one that I'm going to use. I'm going to import k neighbor classifier, initialize k neighbor classifier with n neighbors equal to 15. I'm going to fit extend wide train, and then I'm going to use this knn.predict. So let me do that. So it's done. Next, I'm going to do a model evaluation. So all these things we were talking about, right? Confusion metrics, accuracy, and all that. So let's just do that using certain measures from sklearn.metrics. Okay, on the data that we just trained. So you see the classification accuracy comes to be 0.95, and this is my classification report. This is my confusion metric. Okay, so far so good. Now what I'm going to do is, so what are my errors? Errors are these two, right? 3 and 2. So these are my false positive, false negative, as I term my classes. So now what I'm going to do is, I'm actually again I'm trying to look at some optimal value of k. Okay, so let me see what I'm doing over here. And for that, I'm going to use a function called as np.range, so which takes 2 parameters or 3 parameters: the start value, the stopping value, and the step of increment. So in this case, if I just run this, it will generate me values like 10, 8, 6, 4, 2, because I am reducing by 2, and it will not go beyond 1. So 1 is the ending point. Okay, so why I'm doing this now, I am applying from 1 to 100, and I want to go and create neighbors from 1, 3, 5, 7 this way, and I want to actually see that which one is giving me best classification accuracy. So what I will do is, for different value of the neighbors, I'm going to run this algorithm and see what is the basic change. The basic change is, I am looping. So I have this array has now maybe 50 values, and for each of these values I'm going to run this k nearest neighbor. And what I'm going to do is, I'm going to pass this integer value as a parameter, okay, to this algorithm, and I'm going to fit it. Then I'm going to look at the knn score, which is nothing but the classification accuracy. Okay, so it gives me the classification accuracies. Okay, so I have just put it, but it was not required. Now what I'm going to do is, I'm just going to plot this. So I'm going to use something like a panda series. So panda series is also like a data frame, but it can be used as a series. So you can, anytime you are doing a visualization on time series, so panda series is a very, very useful tool for you. Okay, so you run this and you get a graph like this, which tells me that what is the different classification accuracies that we achieve. So you'll see that highest you can go is around this range. Probably, I don't know, it will be 96.6%. Okay, uh, uh, for different neighbor values. The more neighbor values, more costly your operation is. So probably will be happy to choose something between 10 or 15. Okay, and go for that value. Now probably 15 is not where we are getting a very good result. So probably we'll choose maybe 5 neighbors, and we can get a classification accuracy of 96.6%. Okay, so that's kind of what I had to cover on knn. And here are some assignments over here. So you can go to my notebook and actually give the answers. And as I said, if you get stuck, I'd be more than happy to help you out. Okay, so that's kind of what I had to cover. So now let me probably stop sharing my screen. Okay, So if you have, I think we have like 3-4 minutes. So if you have any questions or anything,
Hello, sir. This is Saidi Salpade.
yes, I.
Yeah, sir. Actually, I am new to this data science. Like I have a little bit idea about classification and this clustering from data mining. But I have asked you these questions in the chat because for a new person like me, how should we start about this data science? Like, is there any book or thing where we will get all this? Because you are talking, but many concepts are very new. Many people don't know. Like me, I don't know much about data frames or all these things. So how can we start? So is there any book on that? If I want to read about R programming or Python programming basics, so can you suggest some material?
Yes, of course. So the Python book I will probably share with the organizers. Okay. So basically, which is by the name, I think, Data Analysis with Pythons. So that is a fantastic book. Uh, so that has a web version also. Okay. Yeah. So but the idea is, Shaili and all others, is that uh, don't don't go in a thing like a bottom-up approach, what we typically call that. We learn Python, we learn R, we learn statistics, we learn mathematics, we learn this, and then we'll start doing the problem. What will happen is that we'll get stuck somewhere there, because these are so deep. I mean, there are so many new things, believe me, I encounter every day. My students ask me and I'm completely stuck, I cannot answer, because it is a vast area, it is amalgamation of so many disciplines. Okay. So the best idea is that pick a problem. Okay, pick a problem and start from there in a top down approach. Okay, then you see that, look at the data, start with the exploratory data analysis. So when you look at the exploratory data analysis, you will have to understand this mean measures of central tendency and measures of dispersion, right? So just look at that part of the statistics. Then you want to do a exploratory data analysis, so you do look at visualization like scatter plot and box plot, right? And of course you would like to know that how to get it imported in a data frame. But these are again like one line of codes. If you have a CSV file available, uh, both R and Python, and I'm sure any other language, will allow you to get the data in similar format. So once you have that exploratory data analysis done, then you start doing this trend test split, try different models, look at different measures or different metrics, and then try to understand what is going on. Okay, so that's more important. Take a problem, start from there, and then read up. So good resources I have already shown you from the Kaggle data science report, right? So you can look at Coursera, you can look at Towards Data Science as a very good set of blogs. I follow it on a regular basis. Okay, and you can also refer to new journal papers, but journal papers will need kind of need more knowledge for you or more practice from you. Okay, so I will ask you to start from blogs. You can look at my Kaggle notebooks as an example. So right here I have given you the notebook examples. The links have been provided by the organizers. You will see that for each of these notebooks, I have provided individual video lectures, because this I run through my students also. So they also get stuck or has this beginner's blue kind of a problem. Okay, so I hope it answers your doubt.
Hi, sir.
Do
And
Salil,
for
there was a,
R programming, just a minute, sir. For R programming, is it
Yeah,
something
yes.
different from Python or same
Of course,
syntax
I
and
mean,
everything?
of
It
course,
would
if
be
you
different,
get
huh?
to,
Yes, yes.
yes, of course, yeah, yeah. So again, I will. So our cookbook by O'Reilly is a good book, okay, but you should look at this ISLR book that I told you, because again, as I said, your focus is not to learn, not be an efficient R programmer. Your focus is to have a data science, a machine learning approach, or having an engineering approach to solving data problems, right? So ISLR will be a good book for you.
Okay, sir. Would you please share these books if any material is available with the organizers so that we can refer later?
Yes, so I will share this notebook links with the organizers, and I will also share these books that I talked about, and also the corresponding video lectures of these notes. But
Okay. Overall,
I will encourage you to do the assignments. Okay, if you're really interested,
Shiny
and
ma'am, if it is possible, please let
yes, yes. Okay.
people.
Thank you, sir, and sorry for taking your so much time. But I was really curious, and your sessions are really wonderful. Like it would help us to build from the beginners. Though we don't have that much, I don't have that much knowledge, but I'm trying to understand from your video lectures. Thank you so much, sir, and sorry again for
thank you.
taking so much time.
No, no,
No.
it's fine. Is there any other question for sir?
Sir, there was a function called iLock. So can you please again
Yeah, Lord,
just check that?
Professor Amlan Chakraborti having a class night right now, so we can address you later. Saptarshi
Yes,
sir will be there anytime. Okay,
yes, 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 yes.
no issues.
And Saptarshi sir again has a lecture tomorrow, I guess. We won't be, if you have any further doubts regarding this session or the session he will be taking or the session he has already taken, I guess he'll be welcoming questions even then. So thank you, like Saptarshi sir. Like it was a very good lecture session for everyone today, and they got an experience of how to handle Jupyter and how to handle scikit-learn and other open source libraries, Python libraries and other data science. So thank you, thanks a lot. It was a really wonderful session. Thanks a lot, sir.
Thank you, thank
Thank
you.
you, sir.
So next up is our next guest lecturer will be Amlan Chakraborti sir. So talking something about Amlan Chakraborti sir. Professor Amlan Chakraborti is presently professor and director of A.K. Chaudhuri School of Information and Technology, University of Calcutta. Prior to this, he completed his postdoctoral research at Princeton University after completing his PhD from the University of Calcutta in association with Indian Statistical Institute of Kolkata. He has 20 years of experience in engineering education and research, and he is the recipient of prestigious DST Boys Cast Fellowship Award in Engineering Science 2011, Indian National Science Academy (INSA), and Erasmus Mundus Leaders Award from European Union 2017. These are some of the awards which he got, and to name of the vast majority. He has also served in various capacities in various higher educational organizations, both at national and international levels. He has received multiple project grants in the areas of security and in cyber physical systems, IoT, embedded system design, VLSI design, quantum computing, computer vision, and data science from various national and international agencies. He was the principal investigator of the Center of Excellence in Systems Biology and Biomedical Engineering, University of Calcutta, funded by MHRD. He has published around 180 plus research papers in referred journals and conferences, and he is a senior member of IEEE and ACM, IEEE Computer Society, Distinguished Visitor, Distinguished Speaker of ACM 2017-2020, Vice Chair of IEEE SEDA Indian Chapter, and many other titles he deserves. So, without any further ado, I would like to make you the presenter, and so that you can speak on your next lecture session, that is on deep learning fundamentals. And thank you, sir. Thanks a lot for making the time for us.
Yeah, thank you. Yeah, so thanks for inviting me, and thanks to the Department of Computer Science, Professor Prashinjit, and the Department of Computer Science of National Institute of Technology, Durgapur. So I hope that Saptarshi, as always, has given a very interesting session to all of you on the fundamental techniques of data science. And what I will today I will lecture, or I will try to discuss with all of you about the fundamentals of deep learning, where I will try to first focus upon the very basics of neural network, and then I will get into the details of how the convolution neural network and how the deep learning stages works, and also I will try to give you some understanding of the different types of deep networks which are very popular at the present time. Okay, so let's start my presentation. And sorry, yeah. Okay, so I hope that my slide is visible to all of you, right? And I'm perfectly audible to all of you.
Yes, sir.
Okay, sounds good. So this is what is my lecture today, is deep learning fundamentals, and the key topics that I will discuss today are a perceptron network, a multi-layer perceptron, and how the concept of artificial neural network comes up. Then we will discuss about how we can have the performance, how we can understand that how my network is working and what's the performance of my network, what are the metrics, right, and how we can optimize the performance. And obviously the way I do the steps I perform to reduce my error and to optimize my performance obviously involves the gradient descent and backpropagation. And then obviously the basics of convolution neural network, how it works, okay, how the various stages of convolution neural network works. So this is a pretty extensive lecture. I have 90 minutes in my hand, so I will try to give some in very precise way, and some I will discuss in details as per I find the requirement, okay, in understanding the entire concept of neural network and deep neural networks. I also have some slides where you will find that okay, you can ask questions and you can understand once I show the slides to you. So at that point of time, I will give a pause in my presentation, and I will ask, or I will wait for a couple of questions. And obviously, after my lecture, also you can ask me questions. Okay, so the first discussion is on the basic understanding of perceptron, multi-layer perceptron, and artificial neural networks, which are the building blocks of deep learning. So we know that there is a real push, okay, towards utilizing the networks, okay, utilizing the different forms of networks, starting from the very basics like multi-layer perceptron to the very complex like in the convolution neural network, recurrent neural network, adversarial neural network. Okay, so there is a plethora of different type of networks, and if you have the fundamentals, okay, of the networks are okay, that you can understand, right? It is not very difficult for any one of you to understand how this network works, or when you try to build your own network for a particular problem, right? It will be not very difficult for you to build that too. So let's try to understand that how it all originated, right? How the concept of the artificial neural network originated. So it originated from the idea, or from the things which happens in the biological cells, right? In the biological cells, we have the neurons, and what the neuron works, the neurons actually takes your signal. It takes your signal from the different sensory organs, and the signal comes to the neuron in forms of the dendrites, okay, which are the some sort of anterior part of this particular neuron. And then there is a biological function, right, which operates on the signals coming from the dendrites, right, and generates some sort of activation signal or actuation. And this actuation signals, okay, gives the reaction, okay, of the biological, of the biological element or the biological organ or the maybe an entire biological object to interact, right, or to give a response to the signals which is captured. Okay, it may be that okay there is a hot sensation, so you just take off your surface or take off your hand out of that, right? Or it may be trying to understand okay, there is through my vision sensors trying to understand that whether okay, the person who is there in front of me, whether he or she is known to me. So there may be different complexities in all this type of actions, but basically this type of activity, which is basically aggregation of the data coming from the various inputs and trying to take a decision based on the cumulative input, okay, is the driving force, right, to build the structures called neurons or artificial neurons. Now, the artificial neuron, the proposal of artificial neuron was basically done by Minsky, right? Okay, he actually said about the perceptron model, right? And then it was taken ahead by Frank Rosenblatt. So the basic model of perceptron tells that you take the data from your environment, right? And if you see this variable adjustable parameters, these adjustable parameters are nothing but weights. Now what happens is that the inputs which comes from your environment, right, are being combined with the weights, right, and there is a summation, okay, a sum function. And the activation, what was being said at that point of time was basically a simple threshold function. So a threshold function means that, okay, if the cumulative of the weight combined by the input, so these are all inputs, A1 to AP are all inputs, and the W1 to WP are adjustable weights. Okay, these weights are in your control, right? You don't have any control on the inputs. The inputs come from the environment. So your model or your perceptron model basically is defined by what are the weights you are putting for these inputs, right? I will come to this in details when I in my next slides. But what was being proposed in the basic perceptron model is that you try to take the inputs to the weights, right, and take a cumulative of this operation and try to define a threshold. If the cumulative value is less than a particular threshold value, then you give the output or the outcome as a low, right? And if the cumulative value is above a threshold, right, you take an output as a high. So now that particular assumption, which initiated in mid-90s, right, can be very well visualized by this particular figure. So what I show here is that I show that I have inputs, okay, to my perceptron, which are labeled as x1 to xm, and there is a special input which is labeled as 1, right? So what happens here is that you also have the weights which are W0 to Wm, okay, and this particular stuff is completely summed here, which is the equation is given here. So what I have the xi's, which is my input, and wi's, okay, which will be decided by me or by the model, okay, and right, and then they gets multiplied, right, and there is a particular particular input, which is 1, okay, and the weight corresponding to this is W0. So which is a special weight and a special input. Now this input, okay, this entire stuff can be represented by this particular mathematical operation, right, where xi multiplied by wi summed over I equals to 1 to m, okay, and added with W0, right? As W0 is, okay, as the input correspond W0 is 1, so whatever we add is W0 only, right? And this W0 is called it's a special parameter which is called a bias, right? We will know that how the bias influences your model, your neural network model, okay? So then this particular input actually touches this particular okay, node where we place the activation function. This activation function is called a G, and this activation function, why is it called activation function? Because this activation function actually defines the output of Y, okay, or Y kappa, whatever we say. So depending on the nature of the activation function and depending on the value of this bias with the cumulative weights multiplied by the input multiplied by the weights and the cumulative sum with the bias, so it depends on, so the value of Y depends on both the stuff. That means how we choose the function G and what's the value we generate from the inputs and the weights. Now this G is very similar to a threshold function, a little bit different from that, but it will ultimately generate an outcome which will be pretty high, or we will say that the neuron is activated, or the outcome is pretty low, we will tell that the neuron is not activated. So ultimately the outcome of Y, right, depends on how we try to feed this activation function based on the input multiplied by the weights, and obviously the bias also forms a particular component of that, and also the nature of this particular nonlinear activation function. We say this function nonlinear because the slope of the function varies, right? And that's why it's a nonlinear function, and we'll have a detailed discussion on this also. So let's try to represent this in terms of vectors. So what I can represent very easily is that the vector x and the vector w. Vector x consists of x1 to xm, and vector w consists of the weight w1 to wm. Remember that this x1 to xm are actually your inputs, and w1 to wm are the weights, okay, which you have to decide, right? How we'll decide that, we will come pretty soon on that, okay? So now that the entire equation is represented as W0 plus x transpose W. That's exactly the same equation what we represented as xi, okay, xi multiplied with Wi, right? With the input multiplied with the weights. So the input multiplied with the weights, if we try to define in terms of vector, it will be a vector of x and vector W, and it's a multiplication of the x transpose with W. Okay, with that we have a bias W0, and that is the equation. Okay. So now we try to put some values on this. Okay. So now let's put our own choice of weights. So suppose our choice of weights for this particular perceptron is 3 and -2, right? And I choose the bias, which is 1. How does this equation look like? So if I put the values, the equation will look like a very simple linear equation, okay, with two variables, because I have 2 inputs. So it's a straight line, okay. So straight line in the plane x1 x2, right? In the plane where the axes are x1 x2. So this is a simple straight line equation what I can derive once I put the weight, and that's 1 plus 3x1 minus 2x2. So why it's 2D? It's 2D because I have only taken 2 inputs. Okay, these inputs can be considered as features. So my feature space is 2-dimensional. So this particular equation is a 2D line. But if my feature space is multidimensional, but this will be a sort of plane or hyperplane sort of. Okay, so you have to remember that how the dimensionality, okay, how the dimensionality will influence the nature of this particular representation, okay, of this of this neural network function, right? So now if you give a test input now, okay, so I have an equation, right, and I give a test input now. So let us, my test inputs are, okay, minus, okay, so I define the vector x here. So my vector x is -1 and 2. So if I put the value of -1 and 2, right, what you see is that you see, okay, you get a value of y cap based on this, because I've already defined defined this particular okay, that I already have the weights. So as I have the weights, my based on my equation, right? Okay, when I supply the equation with an input value -1 and 2, and the value evaluates to -6. Now what happens is that you can visualize that, okay, you can very, sorry, yeah, so you can very easily visualize that this particular point, okay, this particular line is something which is actually gives equals to 0. And if I put the values of x1 and x2 depending, okay, based on -1 and 2, if I put this, I get the value is -6, right? And this point is on the other side of the line, where actually okay, this equation evaluates to less than 0. And whereas this part, whereas the right hand side of the line, okay, represents the region where it's greater than 0. So what you can easily estimate that this particular representation defines a sort of classification, okay, where if the value is less than a particular, if the value falls in this part of the line, okay, on this half of the line, it's a okay, if the value will be low, okay, or maybe class 0, right? And if the value forms in this part of the line, the value will be high, which is a class 1. So you see that activation function exactly does that. So activation function is a function which will try to based on its property, right? It will try to, it's also called a squashing function. So it will try to push the value into one particular class, right? If the value is below a threshold, and it will shoot the value to another class, right? If the value is greater than a threshold, right? And those are the nature of activation functions, so that the neuron, so that they can tell whether neurons are fired or not. Okay, and it all depends. And remember, it all depends on how you have taken the weights and the activation function. Because if you have a different combination of weights, it might be the same input, could have been on the other side of the line, right? Or if you have a different type of activation function, right? Your cumulative, your output would have been different. So this is pretty important. Okay, why a neural network works according to your to expectation, or a neural network doesn't work according to expectation. Okay, it doesn't work according to expectation because you might have chosen the wrong weights. Okay, so if you go ahead of this and we try to say that, hey, we will, from the perceptron we will go for multi-layer perceptron. So in the previous model of perceptron, we had only an input and an output, right? There was no layer in between. But once we tell that I am using a multi-layer perceptron, what it means is that you are trying to put more layers within the input and the output, right? And that's a name called multi-layer perceptron. Okay. So what I do here is that you follow the same principle. It's a nothing different. It's a same approach, the same computation you need to do. Only you have to just just aggregate more, and you have to go on into more levels. So let us take an example of what is being shown in this particular figure. We have only one hidden layer, right? And this is the hidden layer. Okay. So this hidden layer, actually, this is the input, right? And instead of one output, which was in perceptron model, we have actually added multiple outputs. So we have two outputs here, one y1 and y2. Right? How it works. So as in the perceptron, we had each of the inputs, okay, will be multiplied with their weights, right? And we'll be going to the next layer. Okay, in the previous model, the next layer was the output, but here we have a hidden layer. So it will follow the same process. So the inputs, all the inputs multiplied with the respective weights will be ultimately connected to all the hidden nodes. Now the question is, what's the difference then? What's the difference between each of the hidden nodes? Now each of the hidden nodes will apply different weights. So which means that the weight for x1, while it is meeting z1, okay, will be represented as w11, because the notation I have used here is that wji. So wji means that here j index is for the input and I index is for the hidden node index. So when x1 is meeting z1, the weight will be w11. But when x1 is meeting z2, the weight will be w12. Similarly, when x2 will be meeting z1, the weight will be w21. So you have now two index of weights in the simple perceptron. We had only one index of weight. And the weight only depends on the input. Here the weight depends on not only the input, also the hidden node where the input is now connected, where the input goes, right? So for each different hidden nodes, right, you have different weights for the inputs, and what we have in each of the nodes, if we try to represent in each of the nodes by the term zi, what happens in each of the nodes? In each of the nodes we have a w0i, which means it is the bias. It is the bias for node hidden node I, w0i, and then xj is the input. Xj is the input, okay, and wji is the weight combining the input index as well as the hidden node index. And it exactly does the same type of cumulative sum. Now the question is, again, the question comes to the students, very basic questions. I'm trying to just giving you insights of the very fundamentals of this, okay? And now, why I will choose multiple nodes in the hidden layer, right? Why I will choose Z1, Z2, Z3, Z4, Z5, or that means, or why not I only choose Z1 and Z2? Why I want to choose Z1, Z2, Z3, Z4, something like that? The answer is pretty simple. The answer is that the weight vectors you are choosing is generating your different ways of combining your inputs. So these are actually different decision windows you are creating, right? Suppose, let me give an example, okay? Suppose you're trying to predict that whether the person is healthy or not, right? How you predict? Try to predict that, okay, whether the person is diabetic, okay, whether the person has a fever, whether the person has some digestion problem, okay. So these all will lead to this, but now the question is, you will not get the data directly of the digestion problem or the blood sugar problem, okay, or the body temperature data, okay, or the fever. What you will get the data of some blood parameters, of some body temperatures, which are your x1, x2, xm. So from this x1, x2, xm, right? So to decide whether the blood sugar is there, you will take the weights of the blood parameters, which are like sugar level or something like that. But for digestion, you will take the parameters. You will have the more parameters for the liver functions of the blood. So you see that the Z1, Z2, Z3, Z4, will be the next level of features, which will be combining these features, okay, in a different way, and will try to generate different features. And based on these features, it will come to the decision. So you cannot arrive to the decision based on just on your initial data, right? You need to combine the data, you combine the features in different way and try to create different windows, right? And each of the windows will actually generate a particular inference, and each of those inferences will be again combined to generate the final inferences, and this process can go on and go on. And that's why you can have a multiple hidden layers. So when I see my students work, okay, they many of the times in the initial stages, I find that they just randomly choose that, okay, I take this number of nodes, I take this number of layers. Now, what is the fundamental background of this we need to understand, and that will give you a more control on the network what you're working with. Okay, so now let's come to the output part. So what happens to the output? In the output, it is the same thing, only the activation comes up. So in the output also, for the output, the Z1, Z2, Z3, Z4, and ZD are the inputs. So you combine again the Zs with the Y with the respective weights, which is defined by Zj, Wji. So here again the J comes from the index of Z, and I comes from the index of Y. So for a particular Yi, right, it will have again a bias which is W0, but here it's suffix 2. So in the first layer it was suffix 1, and in the second layer is suffix 2. So you have a different weight, a different bias, and this bias again does a cumulative sum of the weights combined with this particular outcome of this particular hidden nodes, right? And then it goes to an activation layer because I'm now pushing into the output. Okay, and this activation layer will actually decide the value of Y, each of the Ys, whether they will be high or they will be low. So maybe Y1 is for the blood sugar, right? And Y2 is for the digestion disorder, right? So ultimately, based on your hidden layer inferences, you again combine the inferences and again generate the final decision, okay, whether your Y1 or Y2, which one is higher, right? The value, that means which one gets activated. Okay, based on that you can tell that, hey, this is the class Y1, which means it is a blood sugar, or Y2 is activated, which means it's the indigestion problem. Okay, this is a simple example. You can just try to make you understand. Okay. Now, when you look into the activation function, okay, the activation function is nonlinear. Okay, nonlinear means if you look into the slope of the function, this is the slope of the function. If I draw a tangent here, so you see the slope of the function, okay, varies, right? The slope of the function changes. So this is why it's nonlinear, and one of the common activation function is sigmoid, which is an expression that 1 divided by 1 plus e to the power minus x, which is derived from the fundamental function called logit function. Okay, and there are several activation functions. Okay, it's not that only sigmoid is there. There are several activation functions. Okay, like the hyperbolic tangent, rectified linear unit, leaky value, and the softmax. Now each of the functions have their own variations as being shown in the plots. The gradient curves are also shown, and if you see the gradient curves, this is the gradient curve. Okay, this is the gradient curve for the sigmoid, and this is the gradient curve for the hyperbolic tangent. Okay, so the gradient curve shows that these functions changes their slopes, and that's why these functions are nonlinear activation functions. Now, if we look into the sigmoid and hyperbolic tangent, right? There is there are some limitations, okay, in this particular functions. Now, what are these limitations in the activation function? Limitations is that if you look into this activation functions, you will find that if I give the input, okay, if this is my input or this is my input, both the inputs actually have the same y value and the same outcome because the function saturates. So the issue is that you cannot differentiate any appreciable change in the outcome, though you are changing the input considerably, right? You have changed the input from here to here, right? You have changed the input from here to here, but the change in the output is not visible. So this is called a saturation problem, or it's also called a vanishing gradient problem. Okay, so gradient is very important to understand the change. Okay, the change in the outcome, right? So that you can tweak your network properly to have the desired outcome. But once the vanishing gradient case comes up, right, you cannot see any appreciable change. And similar is the case of a hyperbolic tangent also. Okay, the hyperbolic tangent also have a fast saturation. So a value which is input is this or input is this, right? You don't have any change, right? You don't have any change in the y value. Okay, so y values are pretty same. So this is again the vanishing gradient problem. Okay, though there's another difference between the sigmoid and the hyperbolic tangent is that in the case of sigmoid, the low values are 0 and the high values are 1. In the case of hyperbolic tangent, the low values are -1, right, and the high values are +1. Okay. Now this particular problem is taken care in ReLU, right? What happens in ReLU is that in the ReLU the function is max of 0 and z. So what it means is that if the input is negative, then 0 is the maximum of that. So 0, maximum of 0, and any negative number is always 0. So if your input is negative, right, your outcome is always 0, right? Your outcome is 0. Okay. If your input is negative, your outcome is 0. But once the input becomes positive, your outcome follows the input. It's a ramp function. Now this is also nonlinear, right? There may be a confusion, sir. This is linear and this is linear. So why it's nonlinear? It's a nonlinear because it changes the slope here. Because the slope changes here, right? The slope becomes 1 here. So that's why it actually does one change in the slope, and that's why it's still nonlinear. Now ReLU doesn't have a vanishing gradient problem in the positive values. But in the negative values, it still have a vanishing gradient problem because it doesn't, it gives the same outcome for any negative input. So to take care of this, right, the leaky ReLU was developed, right? And leaky ReLU actually gives a slope for the negative values also. The only difference is that the slope is very low compared to that of the positive side. So the slope is around 0.01. Okay, so that is pretty. So the change is very small in the negative axis, whereas the change in the positive values are pretty high. The last one is called the softmax, which is a sort of okay. So when you have some inputs which defined by xi, okay, what you try to measure? You try to measure the outcome, the probability of outcome, okay, of that xi, okay, among all the outcomes. So summation j equals to 1 to n e to the power xj gives you the probability, gives you all the outcomes, okay, right? And e to the power xi is the outcome for the for xi. So there will be several outcomes like x1, x2, x3, x4, x5, x6. Now you try to estimate that what's the probability of xi. So what you try to do, you try to put it to the power xi, right, and try to on the denominator you give the e to the summation of e to the power xj for all the xi's, right? And if you find that this ratio is pretty high, which means that the xi dominates among all the samples, Okay, so this is a sort of classification. It's the outcome. So if you have a good value of this particular ratio corresponding to your class xi, then you can tell that the probable class for this particular estimation is xi. Whereas if xi goes below a threshold, normally below 0.5, right, you will tell that no, this outcome doesn't matches to the xi. Okay. So this is the way how the softmax classify. This is basically a classifier type of activation function, which gives you a classifier type of nature. Okay. So now the very basic question is that if I don't use the activation function, okay, what will happen? So if I don't use an activation function, or instead I use a simple linear activation function, okay, your nature will be always a sort of a linear outcome, or it's more a sort of regression, because what you are doing, you're trying to generate y, which is a cumulative sum of xi's, okay, wi xi. So this nature is a regression nature. Okay, so it cannot actually it cannot actually expose the non-linearity which is there in the domain. Okay, so it cannot change the shape of the bounded. Okay, it can only divide the boundary into some linear way, like the figure in the left. In the left. So the figure in the right, we see that the boundary between the two classes, are non-linear. And to do that, you require this nonlinear mapping from input to output, which has been done by nonlinear function. Okay, and these are the most realistic type of problems what we do normally. Now, what's the role of this weights and bias? Let's try to understand. Okay, so first of all, we have to understand this neural network is a supervised learning technique. So supervised learning technique means that it will have a training data. So training data consists of your data with its level. Okay, so using the data with its level, it will train the network. Right? And what the train the network means, you will try to find or try to adjust the weights and the bias. Once the adjustment is proper, then your training error is very less, right? And that's where you converge. So for example, what I show here, I show a training data on the left, where I show one particular training instance. So the training instance has 3 parameters: 1.3, 3.7, 2.9, and the level outcome is 0. Okay. So now if I feed this to my network, which means that I will feed 1.3, 3.7, 2.9 as the inputs to my network. But my network has 3 inputs. So I feed this to test my network. And what will be the initial weights? My initial weights will be a sort of maybe some random weights. Okay. And now it is very obvious that in the first instance of my network in the training sprint, the training process, when I generate my outcome, I find it differs a lot from the training data, right? Training from the outcome given in my training data. So example given, your training data outcome is 0, and your outcome, depending on your random choice of weights or some assumption of weights, right? When you drive the network with these inputs, you get the value 0.8. So you have a good training error. So what do you do now? Okay, what you have to do, you have to so you understand that there is a problem in the network parameters. So network parameters are either your weights and bias. So you try to modify the weights, right, and try to find that whether your error reduces or not. There is a standard technique of doing this, which is called back propagation gradient descent. Okay. So now, if you look into the figures on the top right and bottom right, there are two things. One is called adjusting weights and adjusting the bias. So adjusting the weights, what it does, it changes the nature of the line, okay, nature of the partition, okay, between the two zones, but it doesn't shifts the way it actually designs the cut, okay, the cutoff, okay, the trade-off point, where we decide that, hey, if something goes beside this, it is class 0, and if something that comes here is class 1. So it cannot shift this particular decision point when you change the weights. So to shift the decision points, what you need to do, you have to work with the bias. So you see what bias does. Bias actually changes the decision point. Suppose that for the first curve, the decision point is around 0.0. For the second point, the decision point is around 2.5. For the third point, it is around 5. So you see the decision point, okay, that means, changes once we change the bias. So the bias shifts the curves left and right, whereas the weights changes the nature of the curve, but it doesn't shift the curve on the input axis. So that's all about the weights and the bias, and that's all how we need to control that. Okay, and this is actually the same thing which you can go on, and you can make what is a full-fledged artificial neural network consisting of multiple hidden layers. Okay, and the big picture is something like this. So this actually, I'm leading towards a deep network or convolution network, but just to give you an idea that you can just go on building the hidden layers, and it can really give you very complex decisions. Okay, like identifying an image. Okay, then convolution neural network, it does in a different way, but let's try to only get that this particular adding up of the hidden layers and the neurons working the hidden layers, can give you can generate a very complex decision. Right, that's all. Okay, so there is this is the question slide. Right now, I ask that ask the participants, to if you have any question, please let me know. Please ask.
So there's a question in the chat box. Ananya Kanjilal ma'am is asking, how do you choose the number of layers and which one is the optimum?
Okay, so number of layers will actually hugely will hugely complicate your network. So it's not good to just actually go on adding the layers, right? But what the layers help you, I've already said, the layers help you to generate abstractions, multiple level of abstraction. Like the example I gave you, right? From the basic BAT parameters, you try to combine them and try to take the decisions that whether it is a case of case of the diabetic, or it is the indigestion, or maybe some other, right? And from there you actually go that whether the patient is really serious or not. So you see that means as I have taken the decision whether the patient is serious or not based on one abstraction from your primary level features with the BAT parameters, and I generated in the hidden layer the next level of abstraction, I have put one hidden layer. But if you feel that you require several layers of abstractions, for example, you tell that, hey, I want to find the cost of the patient. Okay, so your outcome is not the okay, not that whether the patient is in a good condition of health or bad condition of health. Your required outcome is something that you tell that, okay, what will be the cost of my hospitalization? So then you have to add one more layer, because your cost of hospitalization will be again dependent on the nature of your disease. Whether you are okay, that means your disease is that means your disease is pretty high, or your disease is moderate, or your disease is low. So based on that, your cost of hospitalization will be there. So see, if you want to do the cost of hospitalization, you have to add one more layer. Okay, this is an example I'm telling. Okay, so did you get this right? Okay, right.
Sir, let me try to understand, sir. Is it any way related to the number of features or number of dependent variables that a problem is having? Because
so number of features will be defined at the first layer. Okay, because those are the input features. But now how many different windows you need, right? You require different windows from the features. Okay, see, when we come to the convolutional neural network, this will be pretty easy. The only difference between a convolutional neural network and a traditional neural network is that in the convolutional neural network, the windows are patch based. Okay, in the neural network, unless you use some dropout or something, okay, unless you don't, okay, it's a very conventional neural network. Okay, the window is based on the entire data set. Okay, entire input space. So that's the difference, okay, between the conventional artificial neural network and the convolutional neural network. But okay, but actually this is the way you try to develop abstractions. So ultimate motivation is how many, that means what the way you are building up the abstractions.
Thank you, sir. Do we have any more questions for sir, or sir should proceed further?
Excuse me, I have a question.
Okay, yeah.
Hello?
Yes,
the question is, suppose for example, suppose you are doing a research on, say, analyzing the what you call the medical imaging applications. Say, for example, I'm just talking about angiography. Say, for example, now in this regard, like for example, if I'm going for a research on angiography to analyze this, to helping a doctor for analyzing the blocks in the particular what you call heart, maybe in a particular vein or nerve, by using a particular CNN model or ANML. So how shall we decide, like, which is the best neural network model that will be used for that particular research kind of area? So is there any kind of a tools or strategy or something like that?
A very interesting question. Okay, very interesting question. That's why image processing is so interesting, right? Computer vision and image processing is so interesting. So so it depends on your data, it depends on your application, it depends on your okay, that means your cost model. Okay, so I will come to this pretty soon when I discuss the convolutional neural network. So I'm keeping this question aside, but I will surely answer this when I come to the convolutional neural network. Only the hint I want to say is that you have to look into the way the feature space is built up in a given network, right? And the way you want to build your inference engine. So the way you want to build your inference engine is your own process, right? And the way the feature space is built up, okay, is the process given by the network. Okay, so you have to see that your own algorithm of inference engine and the process of building up the feature space by the network, how much close they are, right? The best closest possible network, okay, will be your choice. But again, say it so, right? The question is very important question. It is not so easy. There is no particular thumb rule by which we can say. But but once I come to the end of my CNN lecture, right, you will get some ideas or some of the clues which can give you the initial intuition that, hey, this network can help me better. Okay, I will come to that. Okay, fine.
Thank you.
So yeah, so it's a good questions, and let me move to my next presentation section. Okay, yeah. Close this. Right. So is my screen is visible to all of you?
Yeah, it is visible.
Yeah. Okay. Okay. So I have around 45 minutes. I will try to squeeze this in very small way because I have to move to convolution neural network also. So we know that we have to enhance the performance of the network, and we know that we have to reduce the error, right? What is the error? Error is basically we have a training set, and my network works on the training set and generates its outcome. So we have something called T, which is the outcome in my training data. Okay, and O is the outcome from my network, and I try to do a cumulative. So it is not only for one sample of my training data, it should be done cumulative over the entire sample, and we take an average. So it is something a cumulative of Ti minus Oi square, which is a mean square, and we take a mean of that, which is a mean square error. There is some noise in the background. Yeah, if you can. So so this needs to be reduced and within a limit, and that will be my better performance if I go on reducing this particular difference. Okay, mean square error difference. It's fantastic. Okay, but the mean square error difference is mostly for the cases where you have some values, okay, which are basically regression or prediction type of applications. Basically, when we use the neural network as a classifier, okay, we normally use a cross entropy loss, right? Here we are telling as binary cross entropy loss, but you can extend it, okay, for no more number of classes also. In a binary cross entropy loss, you mean that you have only two classes, okay? Yi may be y0 and y1, okay? So there are two possible values of your y. So this is something like that. That means your loss is yi. Yi is your it's outcome in your training data, and yi cap is your outcome in your network, right? And you try to do yi dot yi log yi cap, and 1 minus yi means the other class, okay, and that also log I 1 minus yi cap, and that you do for all the instances of your training, okay, and that gives you a loss when it is a category, when your outcome is categorical outcome, or it's a classification type of problem, okay, right? And many of the times we use the one-hot encoding in the as your represent the outcome, which tells that okay, if we have five possible classes in the outcome, we will have a vector of length 5, and for the class for the class 1, okay, it will be the first position of the vector will be 1 and rest all will be 0, and for the class 5 it will be the rest all will be 0 and the fifth position will be 1, and this way we can encode the outcomes also, okay, as vectors. And to do this particular minimization, whatever is my error function, we actually try to see that how my error function gets reduced, right? So normally these error functions are convex in nature. The convex in nature means you have a minimum, you have a global minimum of the function. right? And this global minimum will be the least error point. Now, the issue is how I reach the least error point. The assumption is that this is very important. The assumption is that as my error is not least at present, which means that I am always above the minimum. Okay, let me show if I have a diagram. Yeah. So this is my minimum error position. But as my error position is not minimum, right? I am somewhere here or somewhere here. So what I need to do to come to the minimum error position, right? I have to have a fall down in the slope. So it's called a descent. Because if I go fall up in this, if I go up in the slope, right, I will be going away from the minimum. So the term descent means you are assuming the error function is convex, and you are trying to go descent, okay, from the maximum to the minimum, right? And what will be your gradient, okay, of the descent, right? Your gradient can be so you have to take a proper gradient so that you can actually go down this particular curve, right? And the issue is that how fast you move across the curve, which is called the learning rate, okay, gradient multiplied by the learning rate, gives you how fast you converge, or if you do it very long step, you can miss it also. Okay, those are also the issues, right? So the eta, which is okay, if I go back to this function, there is a eta is called the learning rate, right? And delta EWN, so delta E is expressed in terms of the weights. So we have to update the weights, okay, to reduce the error, right? And the updation of the weights and the reduction of the error will be done based on your learning rate. So Wn minus n plus 1 is the weight, which is the weight after update, and Wn is the present weight, and delta EWN is the error which is being estimated with the weights Wn. And now I take the gradient, I do a del delta, okay, del W, del E del W, okay, which is the partial derivative of error in terms of the weights, right? And try to modulate this weight and try to generate the next weight. Another issue is that how often we do this weight. Okay, to do this, we have different techniques. Okay, you know that the entire training set is defined as epoch, right? I can do this update over after one epoch. Means I have run my entire training set, and I've taken the cumulative error on the entire training set, and then I am updating my weight, and then I am again running the next cycle of the epoch. Sometimes this can lead to overwork. So what is being suggested is that instead of going for an entire epoch, you try to go with a batch. Okay, so what you do, you divide the epoch into batches, and you do suppose your epoch is 1000, and you divide it into 5 batches of 200. So you update this particular, do the update of the weights after a training iteration of 200. Take the cumulative error of a mean error after 200 and try to adjust, and try to use the adjusted weights for the next batch, right? And this way your error convergence can be faster. Okay, so this is all, and this is the this is how the derivative is being done. It's pretty simple. The derivative function, which basically assumes that it is a continuous function, but this is basically on the discrete domain, because you have the discrete values of your of your OD, So you see that you can very easily define that for a particular, so this is very, very important, for a particular weight, which is defined as Wi, how you evaluate del E Wi. It's very simple. What you do, you actually take TD minus OD, which is pretty simple, and you multiply that with the particular input for which Wi is the weight, right? And that comes with a negative. Okay, so this is a very simple way how we can actually do this computation of del E del Wi based on the initial error function, which is defined as TD minus OD square, and we take only one. Okay, instead of actually taking the entire n, I take 1/2n. Okay, just to cancel the power of 2 in the derivative part. Okay, so I will take the questions later due to the time. So let's actually, so this I will very quickly move. So now the issue is that, okay, suppose I know the gradient, right? How the gradient helps me to adjust the weights. Okay, so this can be very easily defined by computational graphs. Okay, so you see that this is a computational graph which tells that here this is the equation. Okay, these are the functions. Okay, these are the functions. Okay, the function fx, y, z is defined in this form, and you see you can calculate the gradient of the, depending on the nature of the function, you can calculate del f del x and del f del y, which can be further generated in terms of dq, del q. Okay, so you see that the functions, okay, the functions del f del y is nothing but it's a chain rule. So if you are trying to find the influence of y over, that means for f, what you need to find? You need to find that, so f is a function of q and q is a function of y. So what you have to do, you have to find del f del w, you have to find del f del q multiplied by del q del w. So you see that to find del q del w, so you're trying to evaluate the variation of del f del q, but in doing that you are moving backward, right? You are doing del f del q multiplied by del q del w. So this is called the backward movement. To evaluate the change in f in terms of q, you have to evaluate the change in, to evaluate the change of f in terms of y, right? You have to evaluate, because these are your initial input weights. Remember, these are your initial input weights, right? So but you cannot touch these weights from here. From here you can only touch just the previous outcome. So if you want to do a partial derivative of these weights for this, what you have to do, you have to go backwards. So you have to first evaluate del f del q, and then del q is again dependent on x or y, and that's the way you do, and that's called the back propagation. Okay, so if you go on doing this, you can just, so the way you try to do this is something like this. Okay, so you move the gradient backwards, because at first your L, loss function, is at the outcome, at the end of your network, but you cannot try to find what is the influence of x and y, which is seated at the very initial layer of your network, which are the weights at the very initial layer of your network. How you evaluate the influence of this on your loss function? So first, what you have to do, you have to first do the derivative of del L del Z, where del Z is just the previous outcome. Now you do del Z del X. Okay, assuming that okay, the x and y is just just generating Z, right? And this way you actually do the back propagation, and you can go on evaluating the del L del Z very well in terms of del L del X. Okay, so del L del X can be very easily estimated by propagating from starting from del L del Z, the immediate outcome, to the farthest input like X and Y. So this is called the back propagation, and the way we can, this is an example. I'm not getting into this. You can just get into this example. Okay, I will pass the slide to all of you. You can just go through this example. I'm skipping this due to the time, but the understanding is same. Okay. Now, what I showed here is that we showed that there is no meeting of the outputs, right? But there may be networks where these two neurons can meet, backward, according to the architecture, right, and can form this node. How you do that? So how you do the gradient back propagation then? So very simple. So in the case of back propagation, okay, the derivative here and derivative here will be added, and we generated the derivative here, and then we again go back propagation in the same way. Okay. So as I told that how fast we do this, it is stochastic. Stochastic is that means after each entry you can update, which is very costly. It's a batch. Okay. It's a mini batch. It's a different way you can do that. Okay. So before I get into the deep learning, okay, let me take if there is any questions from the participants. So any questions for the participants? Okay, so if there is any question in the chat window, no, there's no question in the chat window. Okay. So if there are not, okay, let me take the question at the last, okay, because I think I have to finish within 20 minutes. So let me take the questions at the last. Okay, no worries. So now let's go into the after understanding the basics of neural network, how they work, right, and what are the exact steps followed to build the neural network. What I propose here is a deep network. Okay. Now what is this deep? Now what is this deep network? Okay. Okay. So deep network. Okay. So deep network is something which is a neural network model, but the way it works is that it actually, as I said, that okay, you take the blood parameters, you take the then you go to the condition of the organs, and from the condition of the organs you go to the disease, and from the disease you go to the hospitalization cost. This may be the different layers of generating your abstraction or inference. Okay. The deep network is actually a network which actually takes a multiple large number of these hidden layers network. And the purpose is that it actually tries to understand the abstractions which are deeply seated in your data. And the fundamental application of deep network is basically they started with image data. Okay, the convolutional neural network. Though nowadays we use the networks for for our text also. Okay. So the way, and this process is very well followed, following the way our brain abstraction also works. Our brain has different functional regions. Okay, and these functional regions actually does generate different abstractions from your input, right? And it goes on and goes on to generate the very complex abstraction. Okay, and that's the way if I try to compare the intelligence of a brain, still my computer vision algorithms are just like a baby compared to the intelligence what we have in the brain. We can recognize our friend or our relative, okay, just seeing not the front side, just seeing a partial of that. Okay, and maybe I haven't seen him or her for the last 10 plus years, 15 plus years, but still I can recognize that, okay, this is my old school friend, right? Or this is the person who was my neighbor 10 years ago or 15 years ago, right? We do this because we actually don't go into, our brain doesn't work into the simple abstractions. They go with the very finer abstractions, and on that level, on that feature space, it tries to take the decision. So your decision, you have to understand, your decision always is being defined by a feature space. Now the issue is that how better is your feature space and how best abstracted is your feature space, that defines how best your decision can be. If you have neglected some features, if you haven't correctly chosen some features, if you have missed some features, then your decision can go wrong. Okay, so that's the ultimate way that if we can trap deep features, we can take decisions which are pretty complex, and that's the entire crux of deep learning. Okay, so what we see is that we try to take the differential information, threshold differential information, and convert it to edges. From edges we generate the textures. From textures we generate the object information, and from object we classify whether it's an indoor room or an outdoor room, and this is what is deep learning. Okay, so the fundamentals of deep learning is convolution neural network, and the convolution neural network is a patchy operation instead of a conventional neural network, okay, which actually works on the entire input. Which works on the entire input. Which works on the entire input, okay, and tries to which works on the entire input and feed the data at a shot, okay, to the network, right? This convolution neural network actually works in patches. Okay, and this is what is being shown here. Okay, so what I show here is that you see that this is your convolution kernel. Okay, and this kernel works on a particular patch of your image, and these are further shown here. Why? Because in an image, the information is spatially bounded. If there is a pattern, so each of these kernels, each of the convolutions are generating a feature space. You see, there are so if you have n convolutions, you have n feature maps, right? And these feature maps are being proceeded to the next layer, and there will be further convolutions working on those layers to abstract informations which are combining these feature maps. So it's called a higher feature levels. Okay, so fundamental feature levels to higher levels of features, and it goes on and goes on. And there is obviously, it's not that it is just goes on and goes on like that. There is obviously that if we have spanned the space okay, by okay, that is by primary features, then we can actually okay, we can actually squeeze the space, because now we have to look into a larger area of my image. Once I have finished my smaller area of the image using smaller patches, then I have to find that the features among the larger areas of the image. How I do that? Okay, I have to do subsampling. Through subsampling, I can actually reduce the larger image, okay, window within a smaller window. And so the smaller window now is sufficient to examine the larger image space. And so there is a sort of data compression which happens to the pooling layers to make your kernels work on larger space. Okay, and ultimately we stop somewhere, and then it's most important. And then what happens in the neural network? So what I have done extra here in the convolutional neural network is that instead of just throwing the data, okay, and just giving the neural network their capability to extract the abstractions and generate the classifier, I have used the convolution kernels to extract the spatial patterns in my image. And those spatial patterns will be the input to my classifier, which is at the last end of my network, right? And this will feed my network, and my network will work very fine. That's the entire process of convolution. Okay. So this is a filter. This is a simple edge detection filter. All of us know, right? It is a edge detection filter which sits on the pixel, and if the pixel has a very different value compared to the neighboring pixel, compared 4 neighbor pixels, but it will give a high value. Okay, so this is the way the convolution. It's called a convolution. The convolution in the fundamental in the signal processing convolution means that you have one signal is stationary and another signal actually moves and tries to estimate the overlap. Okay, so it's the same way it is done. Okay, the kernel actually work on the patches of the image and tries to generate the information from each of the patches. It tries to extract the patterns from each of the patches, and it generates the pattern information corresponding to the filter. And then with several filters working, and several pattern informations are generated, and they form the feature space, right? So this is one of the example of how we do the convolution features. Okay, so this is also called representation learning. Okay, because we learn the particular data, or we learn the particular domain by representing it in the feature space. Okay, so feature space representation, higher and higher level of feature space representation, actually helps us in learning the particular domain. So now let us see that with the basic operation of convolution, how it works. Okay. So the example what is shown is a 1D convolution. Means that all my neurons on my input data are linearly arranged in one dimension. Okay, and the way the network works is very simple. Okay, it combines two immediate neighbors, x0, x1, and multiplies by weight, and there is an activation function, and generates the y0. Now, if I want to represent this in terms of a matrix operation, how I will represent? I will represent this at y0 is x0 w0, x1 w2, and I will do something on x2, x3, x4, x5 also. But as in my figure, I see that there is no connection between y0 and these weights. I will just put 0 corresponding to the weights. So if you look here, this particular expression, this particular weight combined by input expression is converted to a weight matrix. This is also pretty important. So So what we had in the case of neural network was weight multiplied by inputs. Now we define it as a weight matrix, okay? And you see that this weight matrix, as it is one-dimensional, you have only W0, W1. But if it is two-dimensional, then what it means that there is a distribution across another dimension, okay? So x0, x1 maybe in this dimension, and maybe x0, x2 in this dimension. So you have another weight coming here. So it is not only the weights are in the row, weights are also in the column wise. So the two-dimensional weight vector will consist of coefficients along the rows and along the columns, and that's what is a convolution kernel, the 2D convolution kernel. So from the idea of 1D convolution kernel, we will now have the two-dimensional arrangement of the data, arrangement of the inputs, and these inputs are nothing but your pixel informations in case of the image. The pixel informations are two-dimensional distributed. Okay. So let's actually look into the problem itself. So if you want to try to understand the convolution neural network in a very simple way, this is what is. So you have to identify patterns. And what I have done, I have generated different orientations of the same pattern X and O. Right? Now if we just try to compare this on the basis of your image information, or simple image comparison, I will find that these two images, though they are of the same pattern X, but one is X which is pretty good, another X is a bit retorted. And if I try to just compare the two images, okay, in the normal image comparison, I will find that these images are completely different. Okay, so you see that there are more number of red cells, which means that these are the points where the information differs. So in a normal comparison, they will be different. But if I try to divide the image into patches, and I try to extract the patterns which are spatially located, indeed I will find that there are a lot of common patterns in these two images, like shown in this figure. And now the question is how I extract these patterns, because provided I extract these patterns, I can compare the two images based on the features, because each of the pattern is a feature axis. So I compare each of the images on the feature axis, and I will find, yeah, they have the same feature values, and so they're the two images. So try to understand that what difference the spatial patterns generates by identifying or comparing between the images. So what we do, we actually convolve this particular each of the kernels. So I have three kernels. One kernel exports the patterns where the diagonals are all white. Okay, I have taken a simple grayscale image, and for simplicity, I've given the values as black as -1 and white as +1. Okay. So this is another kernel which actually tries to take the pattern where the corners are 1 and center is 1, and this is another kernel which actually traps the pattern where the opposite diagonal is white. So if we take these kernels will actually, this is the way the kernel will operate. The kernel is simply a dot product of the kernel and the corresponding image patch. Right, and this is the way how it will generate the data, right, and I can represent the outcome as 1, because all the okay, if I take an average of this, I will find this 1, and this one tells me what? This one tells me that this particular kernel and this particular spatial region has a very good overlap. So this feature is very well present in this particular spatial dimension, spatial region. and that is actually populating my feature space. So I put a value 1 in the feature space corresponding to this particular kernel and corresponding to this particular spatial domain. And then I can go on doing this for the entire region of the image. And obviously, I will not find the kernel value 1 in all the regions because the patterns is not present in all the regions. In some of the regions, I will get a good value, but the pattern exactly matches, right? And this is the way I will do for all the kernels, and I will generate the convolution outcome of all the kernels. And you will see that each kernel will have a high value in the particular spatial region where this particular pattern is present. So this is the outcome. So numbers. So how many convolution kernels you use, according to that, the number of convolution outcomes will be there in a given layer. Okay, so that's one part of that. Another part is the pooling. So you try to compress the data, right? The compress the data is that you try to take a 2x2 window, and you can take the average value of the 2x2 window or the max value of the 2x2 window. So this is the max pooling, where you take the maximum value of the 2x2 window. So this is the 2x2 window, and you take the value which is 1. So what it does, the pooling reduces the data. Okay, so you are squeezing the spatial dimension, and the next level of feature extraction will be done on a much larger spatial dimension, because the spatial information is compressed by the pooling. The other thing the pooling does is that it is invariant of minor change in the orientation, which means that suppose the 1 occurred here or here or here, it wouldn't have changed of getting 1 here. So this is also the job of pooling. So the pooling is being done to reduce the space and to pass it to the next convolution layer so that it can work on a larger spatial depth. Okay. Now there is a ReLU also works. Okay, how you use, normally it's a convolution, ReLU, and pooling. So ReLU, as you know, what it will do, it will try to extract only those outcomes of convolutions which are strong, and will minimize the others which are not strong, so that their contribution in the next level is lowered. So the next level of convolution, so the next convolution window, it can easily find that, hey, the features are strongly present in these spatial regions, and the features are not present in these regions, right? Based on that, the next convolution layer will work. So what the ReLU will do, ReLU will actually suppress all the outcomes which are below 0. So all those outcomes will not be contributing in the next layer of convolution, and only the values which are positive will pass on. And so ultimately what we will have the 3 ReLU layers. And that means we have 3 ReLU layers because I've used 3 convolutions. So for each convolution, we will again have the ReLU. For each convolution, we will have the pooling. So in a nutshell, we will have the layers like convolution, ReLU, and pooling one after another. And that works. Okay? And this can be very extended. And can, as I told, it's a multi-level, multiple level of abstractions. So level of abstractions can extend you from one layer of convolution, second layer of convolution, third layer of convolution, and also you can have number of filters in each of the convolution layers. Then lastly, you generate which is called a flattened network. So what you have after a considerable operations of extraction and also working the extractions on larger spatial boundaries, because patch size, that is the relative patch size, becomes bigger and bigger because due to pooling, your space is becoming compressed. Okay, so now this particular feature space, feature values, is sufficient to give you the decision. And so you flatten all your convolution outcomes, and you call this the flattened layer. And this flattened layer, as you are using a label data, can now actually drive a simple neural network to define the classifier. Okay, so now, as is a label data, you know that you have passed X, and you know that you need to convert this outcome to X. So you know that which neurons will have higher weights for the class X, and if you have passed O, then you know that which neurons will have higher weights for O. So that for a case where the features of X are strong, your measure of X will be higher. For the cases where the features of O are strong, your measures for O will be higher. And for this example, okay, you see the measure for X is 92 and measure for O is 0.51. So you accept that this is the class X. And this is the way how neural network works. And this particular neural network can be multi-layer perceptron, can have also some hidden layers. Okay. So this is the full picture. So if you look into this full picture, what do you find? You find that in each layer of your deep network, of a convolution deep network, you have n channels. So these channels means the number of filters. And this dimension, 24 plus 24, means the dimension of your input. So how many okay, your image size. So the image size at the first convolution layer is 24 plus 24, and your number of channels, number of convolution filters are n1. Then you pull it. Then you do a pooling. So it's a subsampling, right? And reduce it by half. And so its dimension becomes 12 cross 12, and you again use that particular n1. And then you go on and doing this, and ultimately you come the flattened layer. And suppose this is a classifier which recognizes your handwritten digits. So you have 10 class levels, 0 to 9. So you train the network. Network training will give you the adjustment of the convolution weights, kernel weights, and will give you the exact kernel weights, so that the exact patterns can be extracted, and the patterns can be sufficient to classify whether it's a digit 0 or digit 5 or digit 9. Now sometimes you can do a regularization. Regularization means that, okay, your training data, based on the training data, you have heavily followed the training data, and due to that, your network is working very good for training data. But you have to remember that your test data will have a variance from the training data. So if your model follows the training data very well, it's called an overfitting. So it will give some error, or it can give appreciable error when you fit the test data. So to handle that, you try to make some errors so that it will always have an error in the training itself, within a limit. Obviously, it's not within a scope. Secondly, this helps to reduce the number of neurons in the network and tries to help the training faster. Okay, so that's the performance of dropout. Okay, that's a dropout. You try to miss some nodes in the multiple layers of network. So this can be extended for the colors also. In the case of color, there's another parameter. It's called it's a dimensionality parameter, and okay, that means, and you can have 3 channels for RGB color, and you can, so instead of a single layer input, it's a volume input, because you have multiple channels. You have 3 layers, R, G, and B. So the kernels will again operate on each of these layers individually and will generate a cumulative outcome out of the 3 layers. Right, and that is being shown here. Okay. Now you tell me that where I gained in the convolution neural network. Why I cannot use my neural network for my image classification? The answer are 2 ways we can do that. First is the neural network, the basic neural network doesn't consider the spatial distribution. it doesn't, okay, it cannot actually correlate with the spatial distribution. Whereas the convolution neural network can work with the spatial distribution. It actually works with the patches. So it tries to restore the spatial distribution. In this process, it also reduces the number of weights you need to train. Suppose you have a 220 cross 220. Okay, suppose the example is given here. Okay, right? You have a 6 cross 6 image dimension, and your 3 is the number of your that means your channels. So you're using a 3 cross 3 kernels, and there are 3 channels. It will be a 3-dimensional kernel, so it will be 3 cross 3 channels. 3 cross 3 kernels. So the number of weights you have to decide is okay. So in the case of a neural network, it will be inputs multiplied by the weights, right? So it will be there will be sort of what we can have. We can have this 6 cross 6 cross 3 number of neurons multiplied by 3 cross 3 cross 3 number of weights, because each input will have a weight. But whereas if we try to reduce, in the case of the image, you are using the patches. So using the patches, what you are doing, you are not taking the entire input and multiplying it with the weights. You are taking a 3 cross 3 input and the 3 cross 3 kernels. So your always parameters, number of weights are always 27. Okay. So you see that obviously there will be a bias, so it will be 28. So you see that due to this patch-based operation, the number of weights of the convolution filter, instead of making the dimension entire of the image, due to the patch dimension, you have reduced the number of parameters in my filter kernel. That's the way you can do, right? That's a drastic reduction in the weights. So this is the example also what I have given. So if you see the example, in this case it is 32 cross 32 cross 3 cross 28 cross 28 cross 6, 14 million parameters in the case of a normal neural network. But in the case of a convolutional neural network, what you use a kernel of 5 cross 5 and the bias 1. So it is a 5 plus 5 and you use 6 filters. So it is 5 plus 5 plus 1 multiplied by 6. So 156 parameters. So one for 14 million parameters to 156 parameters, it's a huge amount of savings in terms of training and in terms of the complexity of your network. So these are the very standard networks: LINET, ALEXNet, VGGNet. Their complete definition of what are the ways they work, and what are the number of kernels, what are the number of filters they use, right? And how they try to go in the fully connected network. So you can, these are very you can just have the references, and these are the structures by which we analyze each of these networks. Okay, LINET, ALEXNet are very historical. Now the present is VGGNet, ResNet, which is not shown here. These are the very in the insertion network from Google. So these are the very upcoming networks which the people are using in image processing. So the knobs are hyperparameters. So the number of features, size of the features in the convolution kernel. The number of features is the number of convolution kernels. Size of the features is that what is the dimension of your convolution kernel. Window size and window stride is for the pooling size. Okay, size means how much. What is the subsampling parameter? With the way you do the subsampling, and window stride is that how you move. So it can be stride 1, which means that it just shifts 1 adjacent. It can be 2, which means that it shifts 2 adjacent, and that's the way it's done. And in the fully connected neural network also, how many neurons you're using to do the fully connected neural network. That's the way you define the hyperparameters of your model. So we have discussed about images, but you can also do it for the case of sound. Any two-dimensional distribution is fine with the convolutional network. Actually, 3D CNN is also there for the case of videos, but I'm not discussing this in this particular context. So in the case of sound, it is also the frequency in one axis and time steps in another axis. So it also gives you a distribution in two-dimensional space, and you can also extract patterns in the convolutional neural network for the audio for the audio data. And that's all. I come to the end. I will take the questions later. Just to let you know, all of you, I think you are faculties or researchers from multiple institutes across India. I don't know if we have international participants also. So in our School of Information Technology, University of Calcutta, we are working in multiple domains like computer vision, renewable energy, text analytics, cybersecurity, quantum computing, and obviously Saptarshi, who has just spoken previous to me. He is he's a core part of this team also in my lab, and we are doing multiple projects with hospitals, with collaborative institutes funded by DRDO international funding like USAID, corporate fundings like Intel and TCS, and very recently our quantum subcomputing project, which is on developing a new quantum algorithm for ant colony optimization, which is the paper is uploaded in the archive, and we have got the IBM Research Access Award, the first award for an Indian group in this domain. So that's all from my end. Sorry, I might have extended a bit because my topic was quite extended too, and but I end up here. And if you have any questions, I will be very fine to take that.
Yeah, it was a very wonderful session, Professor Chakraborti. Thank you so much for your listening. But the question which I have asked you at the beginning of it, if you can kindly answer, that was basically like on the medical imaging part. For example, if you do any kind of a, say for example, I'm doing an angiography kind of a thing, and I want to do a research on that, like by using various what you call neural networks techniques, like which would be the suitable option for me to go through it. So that would be definitely,
So presently, if you look into the models, I think presently, if you just want to say that, oh, I want to use a one good classifier, I think ResNet is going very strong in that domain. Okay, people are using ResNet because they have they try to minimize the loss in a very different way. Okay, they have a forward propagation path by which they tries to find the identity operation, of your input and your output, and by that it tries to it tries to extract the features in a much more optimized way. VGGNet is also working good. That means it is a very standard phenomenal prior to ResNet. So prior to ResNet, the classifier was VGGNet, and people are also using the different extension of the VGGNet. You will see that there are VGG32, VGG64, something like that. So it means that they are using more kernels with more features. But sometimes you might do overwork on doing that. Okay. So so the issue here is that means people are nowadays, we have recently published a paper on this CT X-rays, okay, in one of the Springer journal, Springer pattern analysis, where we showed that ensemble network. So sometimes it's a very difficult to say that, okay, that whether your VGGNet or ResNet or Inception, which works better. Okay, you can do an ensemble also. Like we have an ensemble classifiers in the normal classical machine learning. Okay, you can have the ensemble of the deep networks also. So so the basic process is that, okay, you have to understand that okay, VGGNet is pretty standard. Inceptions and ResNet are the two two very strong modifications. of the classifiers. They work in different way. So if you see that if standard virginity is not giving you a good classification outcome in terms of your error, right, in terms of your false positive and false negative, the next thumb rule will be to try with inception, okay, or resonance. Okay.
Thank you, sir. Thank you, sir.
Yeah, that's the thumb rule. Yeah.
First of all, I would like to take the opportunity, sir. Thanks a lot for this wonderful lecture. I time and again say that it is really commendable for all the lecturers to cover such huge topics, such vast topics in just 1.5 hours of lecture. So thanks again, sir. And do we have any more questions for sir? Or we should end this session? Okay, sir. So I guess there are no more questions. People seem to have understood or at least got the gist of what you have tried to explain, sir. Thanks a lot again, sir, for explaining this wonderful topic in such an understandable manner. And this was a great session, sir. Thank you.
Thank you all.
And,
Thank you, sir.
Yes, sir.
Thank you, sir, for not only sharing your invaluable time for us, but also enlightening us with your commendable speech on the topic.
Thank you. Thank you, Doctor. Thank you. Thank you all. And I have tomorrow also. I have a session in the morning. Right. I will try to discuss some other concepts of the deep networks. Okay. So thank you. So I am leaving. Okay. Bye to everyone.